Welcome to today's lecture. So I'm very happy to be able to present you section 10.1 about the Lasserre hierarchy for a system of polynomial inequalities. And that's the first section in the new chapter we will begin today, namely the chapter about linearizing systems of polynomial inequalities. So maybe let me start by telling what is it about. So it's about the object of study are systems of polynomial inequalities. So if what is a system of polynomial inequalities? We understand by a system of polynomial inequalities, we understand the system of polynomial inequalities in several variables. So you have finitely many variables, and you have a finite system. I always mean a finite system of polynomial inequalities, namely real polynomial inequalities, and I mean non-strict. So you have greater than or equal to 0 instead of strictly greater than, right? And so VGIs are real polynomials. So you could also say that G underscore is an M tuple. M is arbitrary non-negative integer. So G underscore is an M tuple G1 up to Gm of polynomials in n variables. So with X underscore here is stands for X1 up to Xn as usual. And yeah, so finitely many polynomials give such a system of polynomial inequalities, and you are looking for real solutions. So each solution would be an n tuple of real numbers, of course, right? And you could also have equations here. So you could say that you could think about what happens if you have also an equation like h of x equals 0, right? That's important for practice, for practical purposes, very important. And actually we will just, the viewpoint we have here, that you should model this equation as two inequalities, just by saying that you have h of x greater than or equal 0 and minus h of x greater than or equal 0, right? And for the purposes, for what we will prove here, that doesn't matter if you treat an equation really as two inequalities. In practice, you should perhaps not do it, and you should have some special way of dealing with equations. And everything actually gets easier for equations than for inequalities. But we won't treat this here. So for us, an equation would be two inequalities. So we deal just with inequalities. And the set of solutions to such a system of polynomial inequalities would be when a basic closed semi-algebraic subset of R to the n, right? Because remember, in 631, we had defined what is such a basic closed semi-algebraic subset. Let me see where it is. That was here, right? And that was exactly such a solution set to such a system. Okay, so yeah, we introduce notation for these sets of solutions, right? So actually, the thing we often used, maybe I should have introduced this notation earlier, but if G underscore is such an M tuple of polynomials, we consider the basic closed semi-algebraic set S of G, which is the set of all x in R to the n, such that each Gi of x is greater than or equal 0. We looked at such sets very often. Maybe I should have introduced this notation earlier. Okay, one can easily imagine that many horribly complicated computational problems can be easily translated into a problem of solving systems of polynomial inequalities. There are so many problems, like combinatorial problems. So you ask some questions, for example, about finite graphs, and maybe this question is very hard to decide. And when you can often easily encode the question into the question whether a certain system of polynomial inequalities is solvable or not, right? So you can imagine maybe that you can express so many things easily by systems of polynomial inequalities that, so if you could efficiently solve polynomial inequalities or just decide whether there is a solution, that would lead to so many path-breaking new algorithms that it seems unlikely that polynomial inequalities can be solved efficiently, right? Okay, but so if you did some complexity theory, we could say much more. We could make this statement much more formal, etc. That is clearly outside the scope of this lecture. So it would be no surprise if it were in general very hard to deal with polynomial inequalities algorithmically. And the proof of real quantifier elimination, by means of which one can, for example, decide whether a given system of polynomial inequalities is solvable, right? Because I could just write down where exists, could use existential quantifiers. I could write down where exists x1, x2, etc., such that g1 of x greater than or equals 0 and g2 of x greater than or equals 0, and so on. The proof of real quantifier elimination would solve this problem, because the proof of real quantifier elimination we gave in Theorem 1.8.17 is really algorithmic. You can really read it as an algorithm to eliminate the quantifiers, right? So we have here a quantifier, an existential one, say over the reals. Here we work just over reals now. And you can actually, eliminate it step by step, right? So you get here a finite disjunction, if you want, and you get here here you don't see it in this proof, right? But if you look at 1.8.14, 1.8.16, that was this little trick. So if you go to a proof of real quantifier elimination, when you will see that it is actually an algorithm, it gives you an actual way of eliminating these existential and universal quantifiers. And of course you have to pay a price, and if you look at the proof, you see the price you have to pay is that you get a really big expression with conjunctions, disjunctions, etc., negations, right? So you get that would have, if you can actually easily program it, right? So it would actually be possible to program it, and certainly some people did, but the complexity is really horrible, right? Okay, so and that gives a little bit a taste of how it is, how these algorithms that solve such general problems like deciding whether a given system of polynomial inequalities is solvable, how such algorithms in general look like. Now there are much better algorithms than the one I gave for the proof of real quantifier elimination. There are much better ones, but still they are usually horrible on examples that are not on any input which is not very, very small. Still, these algorithms are very useful, because even for small input, you would like to do something, right? But in general, they have horrible complexity. So now here we pursue on, so either you have to accept that the input for these algorithms is very small, so you deal just with very small systems, say low degree, not many number of variables, like not many inequalities, right? Either you accept that the system of polynomial inequalities is very small, or you have to accept that you cannot solve all problems. And what we do here, we try to identify a class of problems that one might be able to solve efficiently. I mean, we don't really go to we don't really go the whole way. So we don't really say for this and this and this we have an efficient algorithm. It's more like we say, see for this. So we have a method. We have this Lasserre hierarchy. So for each degree bound D, it gives us linear matrix inequality. We can solve linear matrix inequalities usually very efficiently. The only problem we have is that linear matrix inequalities that are too large cannot be solved because they are simply too large. Right? Cannot be solved in practice because they are simply too large. So we will have a method of, that tries to translate a system of polynomial inequalities in a so-called linear matrix inequality. I will introduce in a minute what that is. That tries to translate it in some way where you have to be very careful what you mean by translation, right? And then we will have some a priori fixed degree bound, and if this degree bound is very low, the linear matrix inequality will be small, and we will have, and in the end results, let's say, for some possibly large degree bound, the linear matrix inequality is very close to what the original polynomial inequality system of polynomial inequalities expressed, right? In some sense, right? And then at least in some cases, right? And then the thing is, we don't go to the end, so we don't say for this and that degree bound it works. We say there is a degree bound. Now it could still be that this degree bound is too large because the larger the degree bound, the bigger the linear matrix inequality, and if the linear matrix inequality is too big, you cannot solve it anymore in practice, right? But at least if you know that there is this degree bound for which it works, then you could say, now I hope that it works also for a small degree bound, right? So there is no obstacle, maybe. There is no theoretical obstacle, at least from our theory. But sometimes there will be obstacles, but we have some results. We say here there is no obvious obstacle. So the only obstacle could be that the degree bound is too large. And then you hope that it works in practice even for low degree bounds. And this, that you have these levels, right? So we have for each degree bound, that's one level of the Lasserre hierarchy. And so in practice, you will make a degree bound so large that you can still solve a linear matrix inequality efficiently while you drink a coffee, let's say. And and you hope that this is enough for solving your problem, and often it is. But sometimes there are theoretical obstacles, and no degree bound will actually work. And and we want to prove that sometimes there are no theoretical obstacles. So that's all we want to do, right? And okay. So we try to identify cases where efficient algorithms for dealing with systems of polynomial inequalities might possibly exist. And our approach will be to relate systems of polynomial inequalities to so-called linear matrix inequalities. before we introduce the letter, we need more notation. Okay? So, namely, if you have a symmetric real matrix, this S stands for symmetric, when we write a curly greater than or equal 0, A is curly greater than or equal to 0, means that A is positive semi-definite, that means A is symmetric, and X transpose mx greater than or equal 0 for all x in R2k, right? And this curly bigger than 0 means positive definite, right? You remember what that means. So it's the same, but here x ranges over all R to a k without 0, and you require that X transpose mx is positive. Yeah, if B is another k by k matrix, we write that A greater than or equal or greater than B, or B less than or equal than A or less than A, expresses that A minus B is greater than or equal to 0, respectively A minus B is greater than 0 is positive semi-definite, respectively positive definite. Right, and then you could also introduce negative semi-definite and negative definite, which we never did, I think. Okay, so that was just old things with new notation. Now, by a linear matrix inequality, and you often say just LMI, right? Linear matrix inequalities are widespread in mathematics, especially in more applied fields, control theory, for example. So many engineers know what is an LMI, what is a linear matrix inequality. If you Google linear matrix inequality, you find lots of stuff, also from applied mathematicians, from engineers, etc. So by a linear matrix inequality, we understand the condition of this form. So the AIs, by the way, I forgot here A0, so that's a typo in the lecture notes. The AIs are, so we have to correct this in the lecture notes, the AIs are symmetric real k by k matrices, and n is a non-negative integer, and so I have such a condition, right? A0 plus x1, A1, that's a scalar multiplication, so x1 multiplies each entry of A1. And so on, is positive semi-definite, right? So in some sense you have an affine linear combination of the AIs, and you require it, and you collect all tuples of coefficients that make this into a positive semi-definite matrix, okay? And now this looks like a linear, effectively it's called a linear matrix inequality, looks linear because there is no product of the xi's, right? But note that there is in some sense a hidden nonlinearity in it, right? And the hidden nonlinearity is that what this means, that such a symmetric matrix is positive semi-definite. You could also say it means that all eigenvalues, the eigenvalues are all real because it's a symmetric matrix, and it means that all eigenvalues are non-negative, right? Now, the eigenvalues depend, of course, in a non-linear way on a symmetric matrix, right? On the other hand, if you had a diagonal symmetric matrix, the eigenvalues would be just the diagonal entries. And so the eigenvalues, so if the AIs are diagonal matrices, it would really be just a system of linear inequalities, right? And should I say affine linear or linear? Let me just say linear in the sense that we speak also of a linear polynomial if it is of degree at most 1, right? Okay. So there is this hidden nonlinearity, so it looks linear but slightly nonlinear. It's really slightly nonlinear because, symmetric matrices, you can diagonalize them. So for each fixed xi, I can diagonalize this matrix, right? I mean, I can conjugate it with with an orthogonal matrix in order to make it diagonal. The thing is that for each x, I might need another conjugation. I need another orthogonal matrix, right? So I cannot perhaps not simultaneously diagonalize it, right? And that's what is responsible for the nonlinearity here. So it's slightly nonlinear, and it turns out that in many applications you need to deal with nonlinearities, right? You can imagine if we are doing real algebraic geometry, we are dealing with polynomials which are highly nonlinear, right? And we have to deal with this nonlinearity, and we want to transform it into something linear. We cannot completely do this, but so linear matrix inequalities might be just the right amount of nonlinearity, right? That we have to admit, and that we can afford at the same time, maybe, right? So linear matrix inequalities, they look very strange when you see them the first time, but turns out that they are a very, very, very good concept. Okay, an equivalent way of writing such a linear matrix inequality is by saying, here we expressed this as a affine combination of symmetric matrices. I could also say that I could also say it's a symmetric matrix whose entries are affine combinations of the xi's, right? So the Lij here are linear polynomials of degree at most 1, right? And because it should be symmetric, I have to require that Lij is Lji for all I and j. So that's another view, right? And we speak of a diagonal linear matrix inequality if in the above each ai is diagonal, or equivalently Lij is 0 for all I different from j. A diagonal LMI obviously just corresponds to a finite system of non-strict, of course, linear inequalities, right? Yeah, that's clear, right? Because the eigenvalues, a diagonal matrix is positive semi-definite if its diagonal entries are non-negative, right? Okay, solution sets of LMIs are called spectrahedra. They generalize the solution sets of diagonal LMIs that are called polyhedra. Right, so polyhedra are somehow bounded by, you could say, flat things, right? But the spectrahedra allow, they are still very special shapes, but they allow for some roundness in their shapes, right? And that's a big advantage over the polyhedra. Okay, consider the LMIs. So let's make an example. Consider this LMI, right, in two variables, and when is this matrix positive semi-definite? Well, I could employ a criterion, namely by 2, 3, 3f. Let me recall this, 2, 3, 3f. It was here. So I take here just a field of real numbers, and when that a matrix positive semi-definite, such a real symmetric matrix positive semi-definite, is equivalent to saying that, all its principal minors are non-negative, right? So if this is an n by n matrix, you have 2 to the n principal minors, right? These are quite a lot, but since we have here just a 2 by 2 matrix, it's no problem. So there is a minor coming from a 0 by 0 submatrix, right? Which is so a determinant of a 0 by 0 matrix is 1. So that gives 1 greater than or equal 0. When we have a 1 by 1 principal submatrices, so I get 1 plus x1 and 1 minus x1. They should be non-negative, and then I get the determinant of the whole thing here. So that's 1 plus x1 times 1 minus x1 minus x2 squared, non-negative, right? So I get this system of inequalities, so I can transform this linear matrix inequality in this system of polynomial inequalities. You see here I go the other way around, from linear matrix inequalities to systems of polynomial inequalities. Whereas my aim is actually to go from polynomial inequalities to linear matrix inequalities, right? But here I go in the wrong way in some sense. Okay, yeah, but you know, what does that define? You know, let's draw this. So here I have Vx1 axis, here Vx2 axis, and here I have -1 and 1. And yeah, here I have this stripe, this green region here is defined by these two things here, right? And then this red thing here, if you multiply this, you get 1 minus x1 squared minus x2 squared. So you see that gives the unit circle, right? Of course, boundary included here. Maybe I should draw also a boundary, otherwise people think it's not included. Right? Okay, so you see the green thing is actually redundant here, and that's of course redundant, and so you get actually just the unit circle. Okay, so, and for the second one, you get here, well, you get again this determinant of the empty submatrix of the empty principal minor. When you get 1 minus, you get 1, you get that actually 4 times here, right? Because it comes also from the diagonal entries. These are the 1 by 1 minors, right? Okay, so, and then you get the 2 by 2 minus coming from 2 by 2 principal submatrices. So you get 1 minus x1 squared, you get again 1 greater than or equal 0, right? And you get 1 minus x2 squared greater than or equal 0, right? From this, from the principal submatrix corresponding to these 4 entries, right? You get 1 minus x2 squared. And then the determinant of the whole thing, you get, you know, rule of Sarus, you get 1 minus yes, so okay, maybe I should draw it in a different way. That was not very good. So you get the product of these 3 entries with plus. Then this gives 1. When you get here x1 times 0 times x2, so which gives 0. When you get here x2 times x1 times 0, which gives again 0, right? And when you get minus x2 squared minus x1 squared, sorry, minus x2 squared, and again 0. Okay, good. So you get actually this, and you see again, this gives again the stripe. This gives again this green stripe I had already drawn, and so this one, and this gives another stripe I had not already drawn, but which also is does not do any harm, right? And you get this stripe here. Okay. Okay, so you see you get again just the unit disk as set of solutions. So both LMIs define the unit disk. Okay. Closed unit disk in the plane. Okay, so there are very efficient algorithms to deal with finite systems of linear inequalities, right? So you might have seen them somewhere, for example, in numerical analysis or in optimization. We saw a little bit of these actually. It was not very explicit, but in 7420, you know, that was this thing here. Okay, so maybe let us simplify a bit to understand what I mean. So let's just take the real numbers. So real vector space, finite dimensional, and so finite dimensional, and E is a finite generating set, and X is an element, right? And when exactly one of the following condition occurs, right? And actually A implies it doesn't matter what it's exactly, but A implies that X is a non-negative or linear combination of elements of E. So it implies that that there exists lambda 1 up to that there exists a family lambda E in E in non-negative real numbers, such that X is sum over E in E lambda E E. Okay. Okay, so and from B implies actually it's easy to see that X is not such a linear combination, or it does not exist such a. And if you look at the proof, you see that actually it's an algorithm to decide whether A or B holds, right? So in particular, by this algorithm, you can decide whether X is a non-negative linear combination of elements from E or it is not, right? But this you can see as a system of linear inequalities. You could say that, you know, this is an equation of two vectors. You can see it as a finite system of equations, right? So you have a finite system of equations. And then you have the inequalities that each lambda E is non-negative, right? And so you have somehow, you can see it as a finite system of linear equations together with a condition that the variables are non-negative, right? And now it's easy to see that many systems of linear inequalities you could actually transform into this form, right? So you can, I don't even want to think about the details, but you can sometimes decide, maybe always, but maybe I just say sometimes decide whether a given system of linear inequalities is solvable or not. Okay? And the algorithm was actually a version of a so-called simplex algorithm. I didn't say that, but it was this, okay? And the simplex algorithm is actually an algorithm that works very well in practice usually, even though if you have very bad luck when you apply it to some worst case instance when it's not efficient, but usually it's very efficient. Okay, so there are very efficient algorithms to deal with finite systems of linear inequalities. We catched already a glimpse of this in the algorithmic proof of 7420. Finite systems of linear inequalities correspond to diagonal linear matrix inequalities. As a matter of fact, which goes beyond our scope, there are still very efficient algorithms to deal with arbitrary, not just diagonal, linear matrix inequalities. In fact, solving a system of linear inequalities in such a way that a given linear objective function is maximized or minimized is a problem of linear programming, LP, right? So linear programming is ubiquitous in science and engineering, and there are extremely efficient linear programming solvers. We can solve, linear programs with 1 million linear inequalities in 1 million variables, maybe, yeah? I hope I don't exaggerate. A more general problem of solving a linear matrix inequality in such a way that a given linear objective function is maximized or minimized is a problem of semi-definite programming. Call that SDP. So SDP is a generalization of linear programming. SDP is still in its infancy, and gets more and more appreciated by many people within mathematics and its applications. And you can solve, for example, at least an LMI of size 1000, right? A 1000 by 1000 matrix in 1000 variables. That should be doable, right? Not 1 million, but 1,000. So you see, it's still a long way to go from SDP to LP, so LP is much more efficient. But SDP is really, I mean, even though SDP solvers are currently not as efficient as LP solvers, SDP allows with just the right amount of nonlinearity, and it's good for algebraic geometry and for many other applications. So for SDP, there are still very efficient solvers, although they cannot yet compete with LP solvers. Okay, consider the following toy system of polynomial inequalities. That will be our main example, or actually our only example for the Lasserre hierarchy in this section. So there will be other examples in the exercise course. Consider the following toy system of polynomial inequalities. 1 minus x1 plus x2 is greater than or equal 0, and 1 minus x1 to the 4 minus x2 to the 4 is greater than or equal 0. Okay, so let's maybe draw the solution set. And okay, so that's the x1 axis, that's the x2 axis. So here's 1, 1, minus 1, minus 1. Okay, so how does this set look like? So first of all, how does this look like? So that's actually a unit ball in the so-called 4 norm, right? The 4 norm of a point x1, x2 would be, you know, if you take this to a 1/4, if you take the 4th square root. Sorry, no, it's not right, sorry. So a 4 norm of x1, x2 would be the 4th square root, so it would be, you take x1 to the 4 plus x2 to the 4, 1 to a 1/4, so a 4th square root. Okay, so that would be what people sometimes call the 4 norm. And that's the unit ball in the 4 norm. So it doesn't look like the unit ball, doesn't look as nice as the unit ball in the 2 norm, in the usual norm. It looks more like a TV screen, right? Doesn't look like disk, it's more like a TV screen. Okay, so let's draw it. I hope okay, I hope that's more or less okay. So that's this thing, and then how does that look like here? So I have here a linear inequality. So that says, you know, 1, 0. 1, 0 is on that. I mean, 1, 0 satisfies the corresponding equation if you put here equal to 0. And 0 minus 1 also. So if you draw a line through these 2 points, a straight line through these 2 points, then, you know, you have this affine half space here that is defined by this inequality. And so all in all, we get here, so all in all, this defines the blue region here. Right? Okay, so that's our set. And you know, it looks like, looks convex, right? With any 2 points, the line segment that joins the 2 points is again in it. It looks like this, but you have to prove this. Actually, it's a little work to prove this. There are different methods, and please think about how to do this. So that's part of the exercise course, but you can prove it's convex, and it has non-empty interior. That's very easy to see, and it's closed. Of course, it's closed, right? It's compact even because it's bounded. That's easy to see. So the terms. So now, but it's a system of polynomial inequalities. It's one that we understand very well. But that's just a toy example, right? In general, we might have 10 inequalities in 10 variables, and then you will just see nothing, right? You cannot even draw in 10-dimensional space. How would you draw such a thing? So the terms x1 to the 4 and x2 to the 4 make that it is not a system of linear inequalities. Here is missing the off, which I have to correct in the lecture notes. Is not a system of linear inequalities. First idea, which is in general way too naive, is to simply replace these nonlinear terms x1 to the 4, x2 to the 4 by new unknowns y1 and y2, and consider, you know, this system of linear inequalities, right? So that's, you know, kind of naive idea. Okay, it's nonlinear, looks complicated, so let me replace it by something more easy. So how are we to know I get this system doublestar? So how is doublestar related to star? Well, first of all, doublestar is, you know, quite useless system of linear inequalities because, yeah, you see, it has just a lot of solutions, and the x's and y's are somehow decoupled and so on. So it doesn't look like this makes a lot of sense, but at least formally every solution of star clearly gives rise to a solution of doublestar, right? By setting, you know, y1 as x1 to the 4, and so you have a solution x1, x2 here. When you can just make out of this, you can obviously make a solution of doublestar. You just put y1 equal to x1 to the 4 and y2 equal to x2 to the 4, right? So sometimes you can see something from this already, right? Because if you're extremely happy, for example, when doublestar might have no solution, I mean, here it has, of course, many solutions, but there might be situations where doublestar has no solution, right? When you might be able to detect it. And then you see that star also has no solution. But these are, of course, very rare cases, right? So here it doesn't work at all. But it's true that the projection, if you take the solution set of doublestar and you project it to the x space, so you take the set of all x1, x2 in R2, such that there exists this y1 and y2, such that x1, x2, y1, y2 solves doublestar. When this contains, of course, the solution set of the original system star, right? Clear, that's the same idea. If I have a solution of star, just set y1 and y2 equal to these things, and yeah, okay, and then you have a solution to doublestar with the same x1, x2, right? Okay, so this projection of a set of solutions of doublestar onto what I call the x space contains the set of solutions of star. The converse is, however, obviously not true, and this does not come as a surprise, since one lost too much information about star. So now we need a little less naive idea, right? The idea is now to add a whole bunch of redundant inequalities to star. before replacing all nonlinear terms by new variables. Okay, so maybe, redundancy, what does it help? Well, on the level of star, it doesn't help, but if you have a lot of if you add a lot of redundant inequalities here, after we linearize, right, after we replace nonlinear terms by new variables, and of course, if you have the same nonlinear term, we will replace it by the same yi variable, right? So this might lead to new information in the linearized system, okay? For example, we can simply add for each, we could simply add a redundant inequality like this. I say, okay, a square of a real number is non-negative. Now let me write here, something like a general polynomial expression of degree 2 with, a, b, c, d, e, f are these general coefficients, right? So a, b, c, d, e, f range over all real numbers. And then I have this thing here, and now I square this. Now I expand this square. Why do I expand this square? So I don't want to linearize now, because when I don't know what to do with this exponent 2 here, when I would get a non-linear system of equations again, of inequalities again. So that's why I expand first here. I expand this thing. I multiply out, so I get a times a plus 2ab x1 plus 2a xc x2, etc. The last thing would be f squared x2 to the 4. So I could expand these inequalities, right? And replace, actually I say these inequalities because for each parameter a, b, c, d, e, f, this is another inequality, right? And I replace not, so I, the a, b, c, d are, I consider them as parametrized, right? So parametrizing the family of inequalities. And I replace not only the term x1 to the 4 and x2 to the 4 by y1 and y2 as I did before, but now I have a whole bunch of other nonlinear terms. Maybe nonlinear, I should write it without space here. By new variables y3, y4, and so on, this would lead to an infinite family of linear inequalities parameterized by a, b, c, d, e, f. The hope is that inequalities that were redundant before the linearization could be valuable after the linearization. One of the problems is that one doesn't generally not know how to deal algorithmically with infinite systems of linear inequalities. We now get an infinite system of linear inequalities parameterized by these 6 real numbers. And how to deal with that when, well, in general, doesn't seem to be a good idea. But now, in this case, happily, there is a way of turning the infinite system parameterized by a, b, c, d, e, f into one single linear matrix inequality. And that goes like this. In order to get rid of the parameters, one first separates the parameters a, b, c, etc. from the monomial expressions. 1, x1, x2, x1 squared, and so on by the following trick. Now, really remember this trick. Rewrite 3 star, right, as a matrix product of row and column vectors in the following way. Okay, so in fact, here I have, a row vector of a parameters times column vector of monomial expressions, right? So I've separated, the a, b, etc. from 1, x1, x2, etc., right? So it's just a times 1. So if you multiply these two with row and with column vector, you get just a times 1 plus b times x1 plus c times x2. So you get exactly this polynomial, right? But I have to multiply with this polynomial again, right? So because I square here. Now I do this, strangely enough, I do this here again, but the other way around. So this time I take here the monomials and here the parameters, but that gives the same thing, right? So why did I do it the other way around? Because I want the parameters to be outside and the other things to be inside, right? Because in the end, the fact that they are outside will allow them to drop them. We will see this later. okay? So, but right now it's just rewritten everything in a strange way. And yeah, what do I do now? Maybe let me copy this. It's just rewritten in a strange way. Okay, so now I multiply these two interior vectors, right? So matrix product is associative, right? So I can, of course, first, even though the initial idea was that it should be read like this, because matrix product is associative. I don't have to put parentheses. And then this is, this is now a column vector times a row vector. It's actually 2 times the same vector. It's a column times row that gives actually a symmetric matrix. You call it also the outer product of this vector with itself. Okay, so yeah, that's one. Yeah, you can see it here. You get this thing here, right? You get this thing here, right? So, yeah, you can check it yourself. You can check it at home, right? And you get this, okay? Let's make a little test. So if I take here the 4th entry and here the 5th entry, right? And I should get this entry here. Is that okay? So x1 squared times x1, x2 is x1 to the 3, x2, right? And you see that here there is a certain pattern, in fact, right? So this appears, it's not only symmetric, but there is a certain pattern in it. So this one reappears here, 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 okay? And this one appears here, here, here. Okay, and this one here, 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 here. And this one here, here, and here. Okay, and I have this one. Maybe let me draw it now this way. And I have this one, this one, this one, this one. And x1 to a 3 is here and here. Yes, I forgot actually. No, that's okay, I guess. Yes, when x1 squared is here, here, here. And yeah, I mean x1 to a 4 is here. It's just there, I think, and x2 to a 4 is just here, and when I have this one and this one, and this one and this one, this one, this one, this one, this one, and this one. Okay. Yeah, you see I have certain pattern. It's not only symmetric, but there are other patterns here appearing, right? If we had just one variable, if we had just x1 and no x2, right? Then that would actually lead to a so-called Hankel matrix, right? It would be of a form that you have here in matrix, and you have the same entries on these kind of, how do you call this? It's kind of diagonals, right? Kind of parallel antidiagonals. But here it's more complicated, right? It's kind of a multivariate Hankel matrix. It's a kind of a multivariate Hankel pattern. So these are very, very special matrices, right? But in particular, they are symmetric. Okay. And I have still, the other thing is just the same here. I have still these A, B, C, D, E, F. So now I linearize again, right? So I will, x1 to a, like before, I mean x1 to a 4 and no, sorry, yeah, x1 to the 4 and x2 to the 4, I wanted to replace them by y1 and y2, right? So let me do this. So, you know, x2 to the 4 here is replaced by y2. x1 to the 4 by y1, right? But when all other, you know, things, so I replace this and this by, sorry, y11, right? And this, I replace by, oh, sorry, y8, x1, x2, I let them actually. I let them like they are. So they stay like they are. 1, I don't change it, of course. When x1 squared gets y3, right? When x1, x2 gets y4, x1 to the 3 gets y6, x1 squared x2 gets y7, x2 squared gets y5, x2 to the 3 gets y9, x1 squared x2 squared gets y12, and x1 x2 to the 3 gets y10. Right, so I have here x1, x2, the original variables, and then I have a new kind of auxiliary variables, y1, y2, y3, y4, y5. Oh, y5 was actually for x2 squared. Sorry, I forgot that. y5, y5, y6, y7, y8, y9, y10, y11, y12. Of course, it doesn't matter how I number the y variables, right? But what is important, of course, that if I replace here the x1 to the 4 by y1, then I should also replace it here by where is it, by y1, right? So if the same nonlinear term appears several times, it should be replaced by the same yi, of course, in order to keep as much information as possible, of course. Okay. A big advantage is now, however, that you can get rid. Okay, and that's, you know, if I do this, I can still read it. I can still read it as a system of linear inequalities, because if I multiply from the left with this row vector and from the right with this column vector, well, that gives again a non-linear inequality in the yi's and the xi's, right? And it's exactly the same as I got before, right? Before I expanded here and I replaced, and here if I do this little trick and then I replace and then I multiply out here, that gives obviously the same thing, right? So you could say, why do I do this? Well, the big advantage, why do I do this trick with this row and column vectors, etc.? Well, the big advantage is now, however, that we can get rid of the parameters ABC by passing over to a linear matrix inequality. Namely, the above is valid for all A, B, C, D, E, F, of course, if and only if this matrix is positive semi-definite, right? I mean, by 2, 3, 1, B, I mean, that's, of course, that's trivial, right? That's just how positive semi-definiteness is defined, right? So this vector X here is plays the role of this vector a, b, c, d, e, f. Okay, so the above is valid for all a, b, c, etc. if and only if the of this linear matrix inequality is positive semi-definite, right? So, linear inequalities are much nicer than linear matrix inequalities. But if I have a system of infinitely many linear inequalities, I might prefer a single linear matrix inequality instead of this, yeah? I might largely even prefer that. Okay, so yeah, so that's why we get rid of the parameters. That's great. We have to pay a little price, namely we deal now with linear matrix inequalities instead of linear inequalities. Okay, so I get this linear matrix inequality. But that's not the end of the story, because there are other redundant inequalities that one could add before the linearization, for example. So in order to keep as much information as possible. For example, one could multiply this inequality 1 minus x1 plus x2 greater than or equal 0 from the original system star by a square of a general polynomial of some degree, right? I could, for example, maybe I should have said, why did I take here like a general quadratic polynomial? I could have taken something different also, right? I could have added, I could have taken a general cubic one, or just add one cubic term or something, right? Yeah, that would be maybe even better. It would introduce then more yi's, more auxiliary variables yi's, but maybe it's better in the end, right? Okay, so that was a choice, of course. I didn't want to get too many yi's, but I did want to get some new information, so that, because the original idea clearly didn't work. Okay, so that's of course a choice, right? That was a choice. And now I have also a choice. I could multiply one of the inequalities from the original system by such a square, right? I could again take a square of a quadratic polynomial expression, right? Or of a cubic one, or, I choose now, because I don't want to have so many yi's, I choose now to take here just a linear polynomial. So I choose to take just an expression like a plus b x1 plus c x2, where a, b, c are now the parameters. And then I square it, right? Because the square of a real number is non-negative. And I get these redundant inequalities, right? Yeah, and if I took here already a quadratic expression, then the total degree of this thing would be 4 plus 1, 5, right? And then I would have needed more new yi's and so on. But, I don't want, I thought it's maybe not good. I'd rather use the yi's that we already have, because if new yi's appear that don't appear here, then, it's also like, you should maybe make appear the yi's as many times as possible. If there is a yi that appears only once or only twice, there is a danger that there is too much freedom for choosing this yi, and then maybe the linearization has too many solutions, like it did in the original naive idea, right? Yi's appear only once in the linearized system. Yeah, that's just a guess that this could be good, right? So I multiply with this, okay, and then we could again, could again expand it and linearize. So expand with square and then multiply it out with this here, distributing it. And then, of course, if I have the same nonlinear monomial expression, I would replace it by the same yi as before. Of course, I wouldn't take another y. I said that already many times now. I would reuse some of the yi from before, of course. to get another infinite family of linear inequalities. But we again apply our trick that will lead to an LMI, and where we can get rid of the parameters A, B, C by doing this in the following equivalent way. We write 4 star as it's the same trick. So if I hadn't this thing, then it would be really the same trick exactly, right? So it's parameters as a row vector times monomial expressions times as a column vector, and here the other way around, right? So now the only thing is that I multiply here with this thing, with this polynomial. So I have to multiply at some point here also. Now I want the parameters to be outside because I want to get rid of them. So I have to put this somewhere, and my choice was to put it here after the first vector of parameters here. I put it here, but does that make sense? That's row vector, it's a 1 by 3 matrix. But this is not a 3 by something matrix, so this cannot be matrix multiplication. Looks like it cannot be, right? At least, yeah, that wouldn't make sense if I put parentheses here, right? So this must be meant in another way. And the way it's meant is like you put parentheses here, right? So when this is a matrix multiplication here, right? That gives again, this kind of Hankel-like matrix. This gives 1, x1, x1, x1 squared, x2, x2, x2 squared, x2 squared. No, sorry. 1, x1, x2, x1, x1 squared. No, that was wrong. Sorry. That was x1, x2, x2, x1, x2, x2 squared. Okay. So this is this matrix, and I multiplied with a scalar, right? That's a scalar product, right? So 1 minus x1 plus x2 times this matrix just means multiplying each of the 9 entries here with 1 minus x1 plus x2, right? Yes, you could also put the parentheses. I mean, I wouldn't do this, but by the rules for by the rules of how you can calculate, you could also put the parentheses here, right? And you could multiply this that would be a scalar times a vector, and then this is a vector times that's the outer product of 2 vectors. You could also see it like this, but in the end it will all lead to the same thing. In the end, this will be a matrix of a certain structure. This time the entries will no longer be monomial expressions, but they will be polynomials. And then I can get rid of these parameters. Okay. Okay. Good. So let me copy this. Okay, linearizing this. So yeah, I can now, I will get rid of this ABC by saying that this is a linear matrix inequality. So let me look just at this expression here. So this is this times this. And now I have to multiply this, right? So let's just do a sanity check. So let me look if I got this entry right. So this entry should be 1 minus x1 plus x2 times x1 squared. So I get x1 squared minus x1 to the 3 plus x1 squared x2, right? So that should be okay. So please check all the other entries also. Okay, and when we obtain the following LMI, so when I linearize, and again, let me just do a sanity check. Let me see if I got this right. So the minus x1, x2 squared, I have to replace by, or the x1, x2 squared, I have to replace by y8, right? Was that the thing I did before? Let me see. x1, x2 squared. That was actually colored in blue before, so maybe I take a blue color here. So x1, x2 squared should be replaced by y8. And yeah, that's what we did before also, right? Okay, and you can check everything. Please check everything, right? And when I get this matrix, okay, so a plus 1 comes from here. I've slightly changed the order, I think, here. So I get this matrix. And here you see I don't get all the yi's from before. Before I had y1 up to, where is it? y1 up to y12. And here I get only up to y9. That's because here that was a linearization of something where all monomials up to degree 4 appeared, right? Whereas here only the degree 3 polynomials can appear here, right? You know. Yeah, but and if I would have multiplied here with a square of a quadratic expression, then all degree 5 polynomials would have appeared. So in some sense, so I cannot avoid here really that it's not exactly the same yi's appearing in both linear matrix inequalities for parity reasons, right? So you see the yi's corresponding to the degree 4 terms were y2, right? y12, y10, y1, right, and y11. So 9, 10, 11, 1 and 2, yeah, y1, y9, y10, y11, y1 and y2, they don't appear here, right? They don't appear here. Okay, good. So finally, we could also add redundant inequalities stemming from the inequality 1 minus x1 to the 4 minus x2 to the 4, right? So we could multiply it by a square of something, right? But yeah, then we would, because this has already degree 4 here, we would need new yi's, right? So in general, this is certainly good if we do it. But maybe then we should have taken higher degree things for the other things as well, right? Well, so let's just try not multiplying it, right? Or we could say we multiply it by a square of a general polynomial of degree 0, you could say, right? And yeah, when, I have just one parameter, I have just, a squared, a is the only parameter, a squared minus x1 to the 4 minus x2 to the 4. And after, getting rid of a is here very easy, right? And if you do the same game as we did before, we arrive exactly at the same thing. We arrive at the thing that this 1 by 1 matrix should be positive semi-definite. So it's just a linear inequality. That means that just with after linearization, this is y1 and this is y2. So this linear inequality should hold, right? If you want to see it as a linear matrix inequality, then see this as a 1 by 1 matrix, because we had one parameter only. So this leads then to this linear inequality, right? So that we had already in Doublestar, and which can be seen as an LMI of size 1. All in all, we consider now our following system of 3 LMIs of sizes 6, 3, and 1 respectively, which could easily be written as a single LMI of size 10 by forming a block diagonal matrix. Okay, so let's see. So that was the thing we had, right? So we get these 3 inequalities. If you want, you could just, I said that one can deal with this using semi-definite programming, whatever this is exactly, but sometimes people say that the feasible region of a semi-definite program is defined by one linear matrix inequality, but you could, of course, define it by one linear matrix inequality just by taking, just forming block matrices. So you take these things, and you form a big, okay, so here's no place, so and you form a big block matrix. So you have 3 blocks, right? One of size 6, one of size 3, one of size 1, diagonal blocks, and you fill up everything else with zeros, right? And you say that this is positive semi-definite, right? And it's quite obvious that this just amounts to say that the individual blocks are positive semi-definite, right? Okay, but in practice, a semi-definite solver is happy if you give him the individual blocks, and he doesn't have to find out that it's of block structure, because he will, of course, exploit the block structure usually. So you should leave the blocks like they are actually. But you could express it as a single LMI if you want. It is clear that the projection where the set of all x1, x2 in R2 such that there exists y1 up to y12 such that x1, x2, y1 up to y12 solves this new system, this LMI system. The projection of a set of solutions of this onto the x-space contains the set of solutions of the original system, right? That's clear by construction, okay? That's the same story as before. Because each solution of star can be made into a solution of a system square by assigning to each yi, by assigning to each yi the value of a nonlinear monomial expression that has been replaced by yi. In this sense, this new system is a so-called relaxation of star, right? Okay, so yeah, so relaxation means it should be hopefully easier to solve, right? And at least each solution of the original system gives rise to a solution of a relaxed system. And where the original variables have the same value, okay? Conversely, it is not clear in what extent a solution of square might perhaps give rise to a solution of star, right? Because if you have a solution of square, right, you don't know if you can interpret, you don't know if y1 is x1 to the 4, right? Okay, and generally at least you don't know this. First step to investigate this is to find a more schematic way of describing the solution set of this new system. Yeah, we want to investigate this system now, and we need a more mathematical way to speak about it. So this time we will hide the parameters ABC not in an LMI, but in a truncated quadratic module. So we had these truncated quadratic modules, 9 to 1. So let's quickly recall them. Here. Yeah, let's recall these quadratic modules. So we had here an degree bound D, a non-negative integer. M was the number of VGIs. So we have again these polynomials G1 up to Gm. We artificially set G0 to be 1, constant 1 polynomial. That will be a good thing for technical purposes. And the idea is now to look at such quadratic module expressions here, right? And the multipliers Pij squared should be, the Pij should be bounded in degree such that the degree of this Pij squared plus Gi is at most D, right? And so I take D minus degree Gi half. So that's here I don't require that the degree of Gi is less than or equal D. Technically I don't require it, so it could be also negative. But it is a half integer, right? It's an integer or a half integer. And if Gi is not 0, when this is well defined, if Gi is 0, when I set it to be minus infinity, and if Gi is 0, I don't need the corresponding Pij's, right? So, or I could say they are 0 also. When we denote by m G1 up to Gm, the quadratic module generated by G1 up to Gm, and the detruncated quadratic module MD of G1 up to Gm associated to G1 up to Gm was defined like this, right? So you take such sums, and here we have these sums of squares here of bounded degree bounded by Ri. So here was another way of defining them, saying that you take here sums of squares times Gi, which are bounded in degree by D. Okay, so these were the truncated quadratic modules. Note that before we came up with the idea, and what we formed actually was quadratic module like, right? Because here we took a square of a quadratic polynomial expression, right? And here we multiplied something with a square, right? It's only that we didn't add these things, right? In a quadratic module, you add them also, right? Because you want, because in the end you want to edit this convex. But we had produced with certain infinite systems of linear inequalities in the x1, x2, y1, y2. If we take this time really redundantly also sums of these linear inequalities, we could have added more redundant things here by adding such things, right? Taking such a thing for certain ABC and adding it, to this thing for another ABC and some DEF, right? And so when it would really be quadratic module, like if you also add, and we could have done this also, right? But we wouldn't have known how to turn this then into a linear matrix inequality, maybe. But on the level of infinite systems of linear inequalities, we could also have allowed such sums to get even more systems of linear inequalities, but that wouldn't have had an effect for a solution of a system of linear inequalities, of the infinite systems of linear inequalities, right? So that would really be redundantly, right? But we observe that we effectively would have added when linearizations of the inequalities p of x greater than or equals 0. For each p in, what did we actually do? It was actually the 4 truncated quadratic module associated to G1, G2, if you think about it. That's exactly what we did, right? Where G1 is this polynomial and G2 is this polynomial. And then how can I then express this linearization? So for the linearization I had this x1, x2, y1, y2, right? And I could do that simply in the following way. I could say I have a linear function from the vector space of polynomials of degree at most 4 to R. That's, so we have here a monomial basis, right? You require it that it maps 1 to 1, the constant 1 polynomial to the real number 1, right? Because, in our linearization, 1 was, or a constant was replaced by a constant, right? 1 was replaced by 1, right? We did of course not replace this 1 by a new variable y3 or something, right? So that's why we require here phi of 1 to be 1, and then phi of x1, phi of x2, and so we don't prescribe, right? Phi of x1 to the 4, phi of x2 to the 4, right? So, and then I just say that phi of p is non-negative, right? That's our linearization. And instead of variables x1, x2, and so on, I have now the phi of x1, phi of x2, phi of x1 to the 4. And in some sense, these are variables. You could say phi is the variable. Phi is my new variable because such a linear function is given, it's uniquely determined by its values on the monomials, right? And so these and conversely, if you prescribe values on the monomials, you get a linear function that realizes these. So my variable is this phi actually, right? I prescribe phi of 1 is 1, and these are my unknowns in some sense. And if you write here phi of p, that's exactly the linearization then. Knowing that the linear function phi can be uniquely determined by arbitrary prescribed values on monomials, we see easily that square can be identified with a state space. So I could say that I take all that the solution set of, I should maybe say that the solution set of square can be identified with a state space. Okay, that's a very important point, so please think about that. Okay, please think about that. So what was this state, right? Maybe I should have a reference to the states here. But the state was, let me say here. Let me put here reference to a state space in the lecture notes. So what was this? This was S of R x1, x2, 4, M4, G1, G2, 1. This was a set of all linear forms on the vector space of polynomials in x1, x2 up to degree 4. So that's the dual space. This star indicates the dual space, the set of all linear forms on this vector space. That means the linear maps from the vector space to R. That map M4, G1, G2 into the non-negative numbers. That's actually a convex cone mapped to the non-negative numbers. And phi of 1 should be 1. Yeah, that was called the state of a triple, this vector space, this cone in the vector space than this element of the vector space. Often this was a unit for the cone, but it doesn't have to be, right? Okay, doesn't have to be. Definition was general. Okay, and so we see that we could have, this solution set to this linear matrix inequality in some sense can be identified with this LD of G here, right? So we define that in general, if D is a positive integer, I take it positive because I need it here to be positive. Actually, here it could still be non-negative. So if D is a positive integer, M is a non-negative integer, G is an M tuple of polynomials, when LD of G is the state space of vector space of polynomials up to degree D in the variables x1 up to xn, truncated quadratic module associated to G1 up to Gm, comma 1, constant 1 polynomial. That's the degree. Okay, here I see here I need also D to be positive, otherwise it doesn't make sense, because otherwise, no, non-negative would here be okay, because 1 has degree 0. That's the degree D state space associated to the tuple G, and as D of G, that is actually this projection, right? That corresponds to this projection, right? Please think about this, it's an important point. That corresponds. That's a more mathematical way to speak about this projection, right? So we phi of xi's are, this corresponded to little x1 and this to little x2. And that was y1, y2, etc., right? So this projection here, right? As D of G, this is the degree D Lasserre relaxation associated to G. So it was Lasserre's idea. He didn't speak about it in terms of states usually, but he spoke about it in terms of linear matrix inequalities and so on. So this degree D state space is a subset of R of a vector space Rxd, of course. No, sorry, of a dual space of it. And Sd of G is a subset of R to the n, of course, right? Maybe it would be helpful to write this also in the lecture notes. And if you want to identify, or if you choose an isomorphism to some R to the n here, a vector space isomorphism, then we were defining what is a spectrahedron here. That's a solution to a linear matrix inequality. And you could also define what is a spectrahedron in a finite dimensional vector space. That would be well defined via this isomorphism, and it doesn't matter which isomorphism you choose, right? That's easy to see. So you could say something is a spectrahedron if and only if its image under the isomorphism is a spectrahedron, and then that wouldn't depend on the isomorphism that you choose, actually. Okay, so in this sense, we have seen more or less, right? It's clear from the example that LD of G is actually would be a spectrahedron inside here, right? Whereas SD of G is a projection of a spectrahedron, right? It's a projection of a spectrahedron, and it's exactly like before, right? And concretely, you could define the LD of G using linear matrix inequalities in these things here, right? And this would then be the projection onto the x coordinates or something. Now everything is more abstract. Let's think more like in this abstract sense now. That will be better for the theory, right? But if you want to do it in practice, of course, you have to work with linear matrix inequalities. Okay. So that's the degree state space. I was thinking about calling it the degree D Lasserre spectrahedron. And this would be the degree D Lasserre relaxation associated to G. That's a projected spectrahedron. Okay. And now let M be an M tuple of non-negative integer. No, sorry, yeah, that's not what I wanted here. So M should be just a non-negative integer. Okay. And G should be an M tuple of polynomials in n variables. Okay, and for each positive integer d, LD of G is obviously a convex subset of a real vector space. I said already it's in some sense a spectrahedron, right? But it's anyway, what is really, without further ado, everybody sees that it's a convex subset of this dual space of Rxd. And for each positive integer, I mean, yes, that would be even okay for non-negative integers d if I had defined it for non-negative integers d, but this makes sense only if d is greater than or equal 1. And as d of G is a convex subset of R to the n, because, projection of a convex subset is again convex, or you can easily prove it. It's convex because of A. So S of G, the basic closed semi-algebraic set associated to G, is contained in SD of G for all d in n, since the evaluation at x, right, so this map, that's actually a linear map from this vector space of polynomials of degree at most t into R. This evaluation at x is a degree d state, right, for each x in SG, right? That's because, the elements in the truncated quadratic module, MD of G, they are, of course, non-negative, or, they are non-negative at x, right? And because x is an S of G. And, yes, and also 1 is mapped to 1, right? And it's linear, of course, with evaluation here. So, since this evaluation is an LD of G, we have at capital X1 evaluated at little x up to ... capital Xn evaluated at little x. So in total we have at little x is an SD of G if x is an S of G. Okay, so that shows this inclusion, right? So, and of course what you would like is, SD of G, you hope at least if D is not too large, it's easily accessible algorithmically, right? By linear matrix inequalities, by semi-definite programming, etc. And you would like to have here, the best thing would be equality here, right? At least if D is large enough, and hopefully D not too large, right? Okay, that's what we want to investigate when is there equality, but maybe that would be too ambitious, because if, SD of G is convex and S of G usually doesn't need to be convex, right? Basic closed semi-algebraic sets need not to be convex, of course, in general. So, let's make more observations. Okay, so... Oh, sorry, that was not the right page. Here is the right page. So let's make more observations. Since SD of G is convex by B, right? I can make this inclusion a little... Well, I can make this inclusion a little stronger by saying even the convex hull of S of G is contained in SD of G. Okay, that's clear. And what is also clear is that SD plus 1 of G is contained in SD of G. So for all D in n, because if you restrict the degree d plus 1 state associated to G to the vector space of polynomials of degree at most d, right? The degree d plus 1 state is defined on the vector space of polynomials of degree at most d plus 1, so I can restrict it to the subspace of polynomials of degree at most d. And it's still a degree, it's obviously still a state, it's a degree d state then, right, associated to G. And that shows with inclusion, of course, right? That shows with inclusion. And yeah, so the situation is the following. So we have here that, you know, I could say like this. We have that this is contained in, you know, in all SD of G. So let's say S17 of G, for example, and then this is contained in S16 of G, and so on, until, yeah, S1 of G. Okay. Yeah, so, and yeah, the hope would be that at some point you have equality, right? The hope would be that, for example, you have here equality, or even better here, right? Yeah, we will investigate if there is equality at some point here. We won't investigate at which point you have equality, right? Which in practice it's of course important at which point you have, if you have at all, right? But that we won't investigate. That's too hard to. That's a very difficult problem. One could give a lot of lectures about, but we don't know even so much about this problem except in special cases. It's, okay, so good. So yeah, so you approach by rising with degree d, right? You get bigger and bigger linear matrix inequalities, and the solution sets, you hope that the solution sets project down to convex hull of SG at some point, right? And if this happens at degree 17, then it also happens at degree 18, of course, because S18 of G is squeezed in between these two here, right? But you hope that it happens for reasonable degree D. Now, in practice, you don't usually start with degree 1, degree 2, etc. You would probably, because 1 is usually too small, right? Why is it too small? Well, okay, let's have this remark. So, first of all, if there is an I such that Gi is a zero polynomial, or that the degree of Gi is bigger than D, then in some sense MD of G does not see these Gi's, right? It's clear that MD of G won't change if you discard this Gi. So if you remove it from a tuple G, right? Because, you know, it's easy to see if you look at the definition of MD of G. Maybe we should even look at it once more, right? So you had this condition here. So if degree of Gi is bigger than D, then this Ri will be negative, and then Pij has to be the zero polynomial here. So these Gi's don't matter actually, and those that have degree too large, and also the Gi's that are zero don't matter, of course. So we just remove them, right? So in this sense, Gi is simply ignored by MD of G, and therefore also by LD of G and ST of G, right? Therefore, one often considers only those positive integers D that are greater than or equal to the degree of each Gi, right? Because otherwise, well, the Gi is completely, yeah, is in some sense not respected, not acknowledged, and it doesn't seem a good idea to discard some of the GIs, right? In general, I mean, in some special cases, it could be that this is okay because because a high degree polynomial might be a high degree polynomial inequality might be redundant when you could discard it, right? But usually not. Good. So usually you would start at a maximum degree of VGIs, right? And you would so with a linear matrix inequality, you would see if it is if it can be done while you drink a cup of tea or while you blink your eye better, right? And when if that doesn't work out, when you make a degree 1 higher, right, or sometimes you make it 2 higher, because sometimes there are, for example, if depends if all degrees of VGIs have the same parity. So if all have a degree 2, for example, when M2 of G is the same as M3 of G. That's easy to see again, right? Because so in this case it wouldn't help to raise the degree by 1 for theoretical reasons already. So when you raise maybe the degree by 2, anyway, you raise the degree and you recalculate everything and so on, and you solve your LMI. And at some point it might take too long, so it might take longer than drinking a cup of tea. And when you are probably dissatisfied, and when you have to think about what to do, right? But when there are still other techniques and tricks, etc., like exploring sparsity and such things, but we won't go into this. Okay. So let D be a positive integer such that now let's say we have such a reasonable D. Usually we start with a reasonable D. Reasonable D would be 1 such that each GI has degree at most D. And let's say none of each GIs is a 0 polynomial, because that we could easily we can easily discard the 0 polynomials. And it's set for technical reasons again G0 to be the constant 1 polynomial. And when for I in 0 up to m we set Ri, you truncate D minus the degree of GI half. So it's a truncation. I guess you say that's floor of D minus degree G half, right? So that's the biggest integer less than or equal D minus degree of GI half. And in 921 I did not apply this floor because there it was not necessary. So here I did not apply this floor here. But the effect was the same, because I said here that Pij should have degree at most Ri, and if Ri is not an if it is not an integer, then it has the same effect. Okay. Now let U1, U2, etc. up to U capital N be the monomial basis of a vector space of polynomials of degree at most D. So capital N is 1 less than the number of monomials of degree at most D in n variables. Then you can write down this set, right? So you can somehow, because the states map always 1 to 1, and so if phi is in the degree D state space associated to G, all its information is contained in in its values on these UIs. So I could just take this tuple and I can identify somehow phi with this tuple. And a set of these tuples can be defined by LMIs, just like before, just like in our example. So I have m plus 1 LMIs, right? Because, 1 for G0, 1 for G1, up to Gm. So, and the sizes are, the sizes are like in the example, right? The sizes of the LMIs, so that's the size of the matrices. That's that's the size of these matrices, right? But they come from these matrices, and these matrices come from these vectors, right? So from these kind of monomial vectors, right? So, this matrix had size 6, it came from this matrix, and it came from this outer product of these vectors, right? And here I took all monomials up to degree 2, because 2 times 2 is 4, right? And G0 has degree 0. And then for the other polynomial, which had already degree 1 here, that was G1 in our example, I could only afford degree 1 here. Yes, because 2 times 1 plus 1 is 3, and 2 times 2 plus 1 is 5 would already be bigger than 4. So yeah, so you see that the dimension of the number of monomials of degree at most Ri, right? That's the length of these vectors, and so the sizes of linear matrix inequalities will be this. So we will be the dimensions of vector spaces of polynomials of degree at most Ri in n variables. Okay. Okay, now so now I want somehow, the states, degree D as state space is somehow defined in terms of the D-truncated quadratic module, right? But there is a way of getting back at least the closure of the D-truncated quadratic module from the degree D state space. So there is kind of a duality, right? At least here, if the degree D Lasserre relaxation of G is non-empty, right? So that's kind of a strange condition, and in some other sources in the literature, etc., you find another condition which just says SG should be non-empty. But SG is a subset of ST of G, and what I actually need is just that ST of G is non-empty. So it's slightly weaker, perhaps, right? Okay. So slightly weaker hypothesis, and therefore slightly stronger statement than in the literature. In this case, so under this very weak condition here, I can prove that the closure of MD of G can be reconstructed from the degree D state space associated to G. And how does that work? Closure of MD of G is the set of all polynomials f of degree at most D, so that are non-negative under every degree D state, right? So the right-hand side of a claimed equation is, you know, with universal quantifier, I can make it into an intersection over all phi in LD of G. Okay, and yes, by the way, this is not an empty intersection, because since ST of G is non-empty, of course LD of G has also to be non-empty, right? Well, so I have this intersection of the pre-images of set of non-negative real numbers under the phi's, under the degree D states. And so the reason why I wrote it in this strange way is just to show that it's closed. Because phi is a linear function, is of course continuous, right? So each phi in LD of G is linear and therefore continuous. You know, we have a unique vector space topology on a finite dimensional real vector space, 7, 4, 18, right? So it's clear what topology we take. It's the unique vector space topology, right? I'm kind of confused. So 7, 4, 18 I said. Is that true? Yeah, here. So if you use topological notions in a finite dimensional real vector space, we tacitly furnish V with its unique vector space topology, which is the initial topology with respect to the family of all linear forms on V. So in particular, linear forms on V are continuous, of course. And yeah, and therefore, so this is a closed subset of real numbers. So pre-image under a continuous map is closed, of course. And if you intersect arbitrarily many closed sets, it remains closed. So that means this is a closed set, right? This is a closed set. So it makes sense to say that it's equal to a closure here. And yeah, so to prove an inclusion now from left to right, since the right-hand side is known to be closed already, it's therefore enough to show that MD of G is contained in the right-hand side. Which is trivial, right? It's trivial that if you have a degree D state associated to G, then by definition it maps every element of MD of G into the non-negative real numbers. So inclusion from left to right up to this closure is trivial, and it's still true with the closure because the right-hand side is closed. Okay, so but the converse inclusion is the main statement here. So for the converse inclusion, we let F be something which is not in the left-hand side, and we show it's not in the right-hand side, right? So it's kind of a contraposition, right? So let F be a polynomial of degree at most D, which is not in the closure of MD of G. And we want to find, we want to show it's not in the right-hand side, so we have to find phi in LD of G, with phi of F is smaller than 0. Okay, so how do we find this? Well, we use separation theorem, right? We use a separation theorem. 735, that was separation theorem for, I think it was, it was for locally convex vector spaces, but our finite dimensional vector space is of course locally convex. So let A and C be convex sets in the locally convex, let A and C be, initially it was written here non-empty convex sets in the locally convex K-vector space V, that don't then intersect, right? And let A be closed and C be compact. When there is a continuous K-linear function, phi from V to R, and there are R and S in R such that phi of X is less than or equal R, less than S, less than or equal phi of Y for all X in A and Y and C. So that was a really good, really useful separation theorem. Now we will actually apply it in a very special case where V is finite dimension. Oh, maybe I should first say that I realized that with hypothesis non-emptiness is actually not really required. I mean, I use it somewhere in the proof here. Guess I use it in the proof here. So that with supremum and infimum are well defined in the real numbers. But in the statement you really don't need it, because if A is empty or C is empty, then this statement here, because it's statement for all x in A, for all y in C, right? This would be a statement about the empty set, and therefore it's true, right? So if A or C is empty, we only claim that we make is that there is a continuous k-linear function phi from V to R, right? But that's always true because you can take the zero function, right? Okay. So I could allow here A and C to be empty. So maybe I should really remove this non-empty here, and then in a proof I have to write something why the empty case is okay, right? So let's say here remove this in the lecture notes. Okay. And by the way, also in another, I mean, here I use 7.2.11, and I think also in 7.2.11 you can probably, I don't have it here, but you can also remove it, I think. I don't remember if it was 7.2.11, but let's put this as a question. Can be remove. So there was kind of the same hypothesis about non-emptiness. And I think I remember that you can remove it for about the same reasons. But okay, so let's look that up and maybe let's correct it in the lecture notes. Anyway, so that was a little deviation now. So what I did here, I mean, I said, okay, let's forget about this S. I just need VR later. Okay, so I just need this R such that phi of x less than or equal R less than phi of y. So actually, it's not astonishing that I won't need VS, because I will apply it with C, a singleton. C will be a singleton, right? So, and actually, because I'm applying it to a finite dimensional vector space, don't care if it's continuous. It's automatically continuous with k-linear function. Okay, so let's see how we apply it. So we find a linear phi 0 from Rxd to R, and an R in R such that phi 0 of G is less than or equal R is less than phi 0 of F for all G in MD of G. So that's our closed set, right? Here we have a closure, and F is not an element of it, so I can take a singleton set with F as my compact set. So when I get this phi 0 here, now, you know, actually from this, okay, because maybe I should write this here, because MD of G is a cone, it follows easily that phi 0 of MD of G is contained in the non-positive real numbers. Let me add this in the lecture notes. Why is this? You know, if phi 0 of some element of MD of G would be positive, then by a scaling argument, you know, I could scale it with a big real number, and I would see that I find another element of MD of G which whose value under phi 0 exceeds R, right? Okay, even if R is positive, right? So yeah, so that's a scaling argument. And now I set phi 1 to be minus 5, and when I see that phi 1 of MD of G is contained in the non-negative real numbers, and phi 1 of F is, yeah, okay. What I also see is that R is greater than or equal 0. Maybe I should add here. And R is greater than or equal 0. That's because 0 is contained in a cone. So phi 0 of 0 is less than or equal R, right? So now therefore I see that phi 0 of F is bigger than 0 and phi 1 of F is smaller than 0. Okay, so now phi 1 looks already like what we need. There is only one little problem. In order for phi 1 to be a state, we need that phi 1 of 1 is 1. But phi 1 of 1, if phi 1 of 1 is positive, then that's easy, right? When we just scale. So we multiply with 1 over phi 1 of 1. And that's still because 1 over phi 1 of 1 is positive. That's easily seen to be a degree D state associated to G. And it has still these properties and when we are done. So the only problem is if phi 1 of 1 is 0. You know, phi 1 of 1 cannot be negative because 1 is in the quadratic module, in the D-truncated quadratic module. So from SD of G non-empty, it follows that LD of G is non-empty, and so I can choose an element in LD of G. Now, let me call that psi. Now, psi plus capital N phi 1 for all positive integers n is in LD of G, right? That's clear because, you know, that's easy to see. It's linear. It maps MD of G to the non-negative real numbers because psi and phi 1 do so. And if you evaluate that to constant 1 polynomial, it's psi 1, which is 1, plus n times phi 1 of 1, which is 0. So it's a degree D state associated to G. And that's true for every positive integer n. Doesn't have to do anything with this. Could also be a positive real number, of course. But I took integers, why not? So choose a big enough integer n such that psi f plus n times phi 1 of f is smaller than 0. Why can I do this? Well, I don't know what psi of f is, right? But I know that phi 1 of f is negative. And therefore, it's clear that I can find this capital N. And when my phi, which I finally want, you know, in LD of G, I take just psi plus capital N phi 1. And it fulfills everything I want. So that was a little trick, okay, to deal with this problem phi 1 of 1, that phi 1 of 1 could be 0. Okay, and when we are done, that's the proof. Okay. So my next remark is really easy, but really crucial also. I will use it all over the place. So if you have a linear polynomial, so that means a degree at most 1 polynomial, and you have a linear function, let's say it's defined at least on degree at most 1 polynomials, could also be defined on higher degree polynomials if you want, with phi of 1 equals 1. And so if you take phi of f, right, then that's phi of x, that's f of phi of x1 up to phi of xn. That's really trivial, right? Because, you write f as a1 x1 plus a2 x2, etc. an xn plus b, where the ai's and b are elements, are real numbers, right? And now if you take phi of x, f of phi of x1 up to phi of xn is a1 phi of x1 plus etc. plus an phi of xn plus b times phi of 1 I can write, because phi of 1 is 1, right? And now I use, linearity. So the ai's, I can put them inside here, b also. And I use, and so I see it's phi of f, right? Okay. I will use that everywhere now. Okay. Okay, so let's go on. Maybe I copy this little remark because it's really important. Maybe I copy also the preceding lemma. And here is already the next lemma. So so let d be a positive integer, m a non-negative integer, and g an m tuple of polynomials. And suppose again this technical condition that as d of g, the degree d Lassere relaxation associated to g is non-empty. So that would be, for example, if s of g is non-empty. When the following are equivalent, and in order to understand this strange condition A here, maybe I should write it in a different way. So namely, what you always have, we learned already, is that the convex hull of S of g is contained in Sd of g. That you have always, right? So always true. And now what I really wrote here is that this in turn is contained in the closure of S of g. Okay. So that means somehow it's squeezed in between the convex hull of S of g and its closure. It looks like, that that's somehow an almost equality with the convex hull of S of g, right? It's somehow it's almost means almost you have what you want, right? Almost you have what you want. What do we want is, we want that the convex hull of S of g is Sd of g. That's the best we can hope for. Okay? And that means that's almost the best you can hope for, up to some technicalities. Because, yes, if a convex hull of S of g is closed, when it really means equality, really what you want, right? But maybe that's in general not true, right? So convex hulls need not always be closed. So if you take, for example, like a half space in the plane, half plane if you want, and union with a singleton consisting of a point outside. Now, if you take the convex hull of this, what will be the convex hull of this? So it will actually be something like this, right? This point belongs to the convex hull because it belonged already to the original set, and all these points, right? But not these points here on the boundary, right? So it won't be closed. Anyway, so that's strangely looking condition, but it says there is almost equality. And the other condition is that each non-negative linear polynomial, each linear polynomial non-negative on S of G is contained in the is contained at least in the closure of a detruncated quadratic module, right? That's also a bit a strange condition because you take here the closure. Okay, that closure is of course taken in a dual space of a vector space of polynomials of degree at most d. That's a finite dimensional vector space, and it's clear what you mean by closure. We have this unique vector space topology on it. Okay, so suppose first that A holds. Suppose, but now let me write it again like it was written here. So suppose first that A holds. In order to show B, okay, let f be a linear polynomial which is non-negative on S of G. So since f is linear, it easily follows that f is non-negative even on the convex hull of S of G, right? You see that immediately. And by continuity, because the set of all points where f is non-negative is is by continuity even is closed, and therefore it contains even the closure of a convex hull of S of G. And yeah, so f is non-negative on the closure of a convex hull of S of G. But when by A, it's also non-negative on SD of G. Yeah, so, but when, you know, phi of f, that was our little standard trick we'll always employ now, is phi, or is f of phi of x1 up to phi of xn. This is non-negative, you know, because yeah, if phi is a degree d state associated to G, when we tuple phi of x1 up to phi of xn, that's actually in the degree d Lassere relaxation associated to G. So it's in SD of G. Yeah, so because f is non-negative on SD of G, this is non-negative, right? But this is phi of f. So this means phi of f is non-negative for all phi in LD of G. But by this lemma here, so this means that f is in the right-hand side of this lemma here. Note also that SD of G is non-empty. So the hypotheses of this lemma are met here. So it's on the right-hand side, so it's also on the left-hand side, right? So, and that's what we wanted. So this implies f is in the closure of MD of G as desired. Conversely, suppose now that B holds and we show A. In order to show A, in order to show this inclusion, right, we turn the logic around a little bit. We say that we have an element of R to the n which is not in this closure, and we have to show it's not in SD of G. Okay. So we have to show that there is that it's not in SD of G. Okay, so how do we do this? So we use again we use again a separation theorem. Here we have again a point. We use actually the same separation theorem that we use separation theorem when we used before. So because we have again a finite dimensional vector space, but this time it's just R to the n. And we have again a point outside of a closed set, right? So we employ it exactly in the same way as before, only that, the linear form on R to the n, we can actually write it as a homogeneous polynomial, right? So let me write it, that's more convenient for our purposes. in 735, you know, it was a linear form in the sense of linear algebra, etc. But here it's a linear form in the original historical sense, right? So, but that amounts to the same here, right? So that's just a homogeneous polynomial, right? Linear homogeneous polynomial. Okay. So we get such a thing f0, and again an R in R. So everything is as before, right? We employ exactly the same separation theorem and exactly with the same, exactly in the same situation. The only thing is that since we have a linear form on R to the n, we write it as a polynomial. So this phi is written as a homogeneous polynomial. And yeah, we don't need Vs again, right? And C is again a singleton. Everything is as before. And so we get this f0 and an R in R such that f0 of y is less than or equal R is strictly less than f0 of x. And for all y in the closure of S of g. Now I set f to be r minus f0, so that's my possibly non-homogeneous linear polynomial still. And we know that f of y is greater than or equal 0. That follows from this, right? So this follows from this. And yes, and from this it follows that f of x is smaller than 0. Okay, so it's just translating this, so getting rid of VR by changing this polynomial. And this is true for all y in the closure of a convex hull of S of g. So in particular, f is non-negative on S of g. Okay, so it seems like I lose information, but I actually don't because, you know, from f non-negative on S of g, I could come back to closure of a convex hull of S of g. But anyway, so in particular, f is non-negative on S of g. And, you know, by B, I've supposed that B holds. Now f is in the closure of MD of g, right? So we have to remember what we have to show. We have to show that x is not in SD of g. We know that f of x is smaller than 0. We have, well, for all, we have, okay, let's see with lemma 10.1.7 here. We have that, that f, okay, f is in this closure. Okay, we were here, but f is in this closure. And now I use the lemma. So if it's in this closure, then f is satisfies this, right? That would be true for every polynomial of degree at most d, but here I use it only for polynomials of degree 1. So when it satisfies this, so I have that phi of f is greater than or equal 0 for all phi in LD of g, right? But this is now employ matrix since f is linear. Since f is a linear polynomial, this is f of phi of x1 up to phi of xn. And since this is true for all phi in LD of g, that means f is non-negative on the degree d Lassere relaxation associated to g. And since f of x was negative, we deduce that x of course is not in SD of g as desired. Okay, so that was really a nice proof. What is still embarrassing though is that we have here with closures, right? The closures are not so easy to understand. So we would have to well, if we wouldn't have these closures here, that would mean that this is exactly the condition we want, that S of g is equal to SD of g. We exactly want to investigate when this is the case. And here we would have a nice criterion in terms of membership in the detruncated quadratic module, namely linear polynomials that are non-negative on S of G should be contained in the detruncated quadratic module. Yeah, that would be nice. So in some special cases we will have this, and in order to investigate when we can forget about these closures, we will simply prove some theorems that say under certain circumstances MD of G is closed and the convex hull of S of G is closed. And to prove this, we need some little tools from convex geometry, which are quite standard, but which we didn't introduce yet. So maybe I should have introduced them earlier. Namely Carathéodoris inequality, for example, we will need. And we need a conic version of it. So here I refer to 241 and 711. Why did I do this? Well, 241 was a definition of a convex set, and we did this over an arbitrary ordered field at that time. Now we need it only for the reals at this point of time, right? So we define convexity, we define the convex hull, and then in 711 we defined a cone, right? 711 we defined a cone, and that we did also in K vector spaces, but here K was actually a subfield of the reals, equipped with the order defined by the reals. And we could have defined this, of course, over arbitrarily ordered fields, but we didn't need it, right? And now we need it only for real vector spaces, right? But what we did not yet define is a conic hull, right? The cone generated by some subset. So let's define it. Let's do it just over reals, because we need it only over reals. So let V be a real vector space and A a subset of V. The smallest cone containing A exists, right? And actually this set obviously is this set of non-negative linear combinations of elements of A is obviously a cone, right? If M is 0, it contains the empty sum, which is 0. So it contains 0, it's closed under addition and closed under multiplication with non-negative scalars. So it's a cone. It's a cone in V. And every cone that contains A obviously has to contain this. And so it's the smallest cone containing A. And we call it the cone generated by A, or the conic hull of A. So it's the analog of the convex hull, right? There is always these two versions. There are the convex sets and the cones, and usually you can go from one to the other, right? And sometimes it's better to work with convex sets, sometimes it's better to work with cones. And one connection, if I say you can always go back and forth between them. This can be done, for example, with the following remark: let V be a real vector space and A contained A a subset of V. When consider the subset A cross 1, so that's just the set of all A, 1 in V cross R, right, where A is in V in A. And consider this subset of a real vector space V cross R, when one easily sees that the convex hull of A is the set of all x such that x, 1 is in the cone generated by A cross 1, in the conic hull of A cross 1, right? Why is this? So, there are two directions. I need a new sheet here. So there are two directions. So if something is in the convex hull of A, then yes, when it's of a form. So there are different ways of proving it, but let me just prove it in this way. So when it's of a form sum I equal m, lambda I xi, where every xi is in A, m is a positive integer, and each lambda I is non-negative, and the sum of the lambda i's is 1. Okay? And when I claim that x comma 1, so if I put here comma 1, I claim that this is a non-negative linear combinations of elements in A cross 1, and that's very easy because this is the sum from I equal 1 to m of lambda I xi comma lambda I, right? Here I use that the lambda I was lambda I sum up to 1, and that's sum I equal 1 to m lambda I xi comma 1, right? And so that's why the left hand side is contained in the right hand side. And why is the right hand side contained in the left hand side? Well, that's also very easy. So taken something of a form x comma 1, which is a non-negative linear combination of elements in A cross 1. So m is a non-negative integer, and the lambda i's are non-negative, and the xi's are in A. Yeah. So if you have such a thing, we have to show that x is in the convex hull of A. Okay, so well, we know that x equals the sum I equal 1 to m lambda I xi. So we would be done if the sum of the lambda i's were 1, but actually it is, because, look at the second component of this equation. That means 1 equals the sum of the lambda i's. Okay. Okay, so that's okay. So we have this connection, and that gives the connection between convex hulls and conic hulls. And with this we can now prove Kara-Theodoris theorem. Okay, so there is a little bit of mess here. Okay, so with this I can prove Kara-Theodoris theorem, which is kind of a standard result in convex geometry, which I could have done earlier. I did it almost implicitly, in fact, without saying it. I did something, in fact, even something stronger. We will see no proof. So Kara-Theodori. So let n be a non-negative integer, V an n-dimensional real vector space, and A subset of V. Okay, and then I claim. So I'm looking at. So there are two versions. There is a conic version and a version for convex sets. And first the conic version, the version for cones. So if X is in the cone generated by A, then there exists a subset B of A of cardinality at most n, okay, such that X is even in the cone generated by B, right? So, this means that X is a non-negative linear combination, a conic combination of elements from A, right? And what this says is, that there is a finite set B such that X is in the cone, subset B of A such that X is in the cone generated by B. That's trivial, right? Because such a conic combination can only involve finitely many elements from A, right? But the point here is that you can do it with n elements, where n is the dimension of a vector space, right? That's the point here. And then, and of course there is an intuition about that. If you're, let's look in two-dimensional space. So let's say I'm in R squared. I have finitely many vectors, okay? And I look at the cone generated by it. And how does that look like? Well, right, that's a thing like this here. Okay. And you see if I have here a point in this cone, I drew here 4 vectors, but you could even draw infinitely many. But if I have a point in this cone, then it seems like 2 are sufficient, right? I need just this one and this one, right? And now in three-dimensional space, the thing gets already a bit more interesting. So let's say I have, for example, in three-dimensional space, so let's say this is R to the 3. And let's say I have 4 vectors, right? 4 vectors, and in fact they should not be all in the same plane, so I think maybe I draw it in that way. Okay, so and now if I have a point in this cone, right? Let's say this one. Then you can find 3 vectors. You can find 3 vectors, and such that a point is in the cone generated by these 3 vectors. And in fact, you can, I draw here. I did draw here this foregone here, right? And if you look at this foregone, right, then you have. Let me draw it here again. So I draw again the same picture in a slightly different way. Now I have this, let's say the point lies actually on the foregone. When, I need just, I can somehow triangulate this foregone, right? I can look at this triangle, and I can look at the blue. No, I need another color, let's say orange. At the orange triangle or the red triangle, and it will lie in one of triangles, right? Let's say in the red one, right? And if a point is not on this foregone, well, then similar argument, right? When you can draw the foregone, I think it's intuitively seems like 3 vectors are always enough, right? It's kind of a triangulation argument, right? I could have triangulated, of course, in the other way, that I consider this triangle here and this one here, right? And then again the point would lie in one of the triangles. Okay, so that's the intuition behind, and so geometrically it makes a lot of sense. Now, the situation, if you have, if you look, so here is a version for convex hulls, So if X is in the convex hull of A, when there exists again a subset B of A of cardinality at most n plus 1, right? Such that X is in the convex hull of B. Okay. So, for example, in the plane, if you have a convex, if you have points in the plane, right? Okay, finitely many or infinitely many. I draw now just finitely many. Okay, so, and this is the convex hull. This is the convex hull here, and when I take a point, and now it should be in the convex hull of 3 points, of 3 of the original points, of black points, right? And it's again, that's such a story with triangulation, right? So, for example, it lies in this triangle. Okay, good. So, and yes. Okay, so, but let's prove this formally now. It's actually very easy to prove. So to prove, no, well, it's not actually, well, there is something, it's easy to prove because we did already a very strong thing long time ago. To prove A, otherwise it would be little work. To prove A, we might suppose that A generates V as a vector space, since otherwise we can pass over from V to the subspace generated by A, right? So, you know, everything here happens in the subspace generated by A, in the linear hull of A, if you want, because the cone of A is contained in there. The cone of B, for any subset B of A, is of course contained in there, right? And if I exchange vector space V by the span of A, by the linear subspace generated by A, then the dimension can only get smaller. And so if I can prove it when for the span of A instead of V, then I get at least the same statement, maybe even a stronger one if the dimension did go down. So without loss of generality, I can assume that A spans V as a vector space. Okay. And now let X be an element in the cone of A. And now I said it's trivial that there is a finite set E contained in A such that X is in the cone of E. That's trivial because a non-negative linear combination can only involve finitely many elements from A, right? So I find a finite subset E of A such that X is in the cone of E, cone generated by E. But, you know, A contained also a generating system for the vector space V, right? And so I could, and actually a finite one because V is finite dimensional. And now, so I can take finitely many elements from A such that they generate V, and I can add them to E, right? So in fact, I can make sure that my finite set E, subset E of A, not only has a property that X is in the cone of E, but at the same time E generates V. So I can make sure both at the same time. Okay. Okay. So now I use 7420. Now I'm in the situation of a very old theorem, which was actually quite strong. That was this theorem, right? And that we used already today. And here E should be a finite set that generates V, and this is the case now, right? And actually X is in the cone of generated by E, so alternative A is true here, right? Alternative A is true, since exactly one of A and B occurs according to a theorem. B cannot occur because A occurs, right? you know, because I said already, if A occurs when X is in the cone generated by E, that's still written here. And if B occurs, it is not, right? So I know that A must happen and B cannot happen, right? But if A happens, when X is a non-negative linear combination of elements of A that form a basis of V, right? So that's the important thing. Now I use really this strong statement here that X is a non-negative linear combination of elements of E that form a basis of V, right? And because they form a basis of V, it can be at most n many, right? And when I take this for my B, so by 7420, there is a basis B contained in E of V such that X is in a cone of B, in the cone generated by B. Or there is this alternative which happens in B, but that cannot be true, right? As I already explained it, actually. And so cardinality of B is n since B is a basis. Okay, so that's because we had this already. We had actually something very strong already. Kara-Theodori is now easy. And now to prove B, a version for convex sets, let X be in the convex hull of A, and we use this very useful remark 10.1.11, right? We use that one. So if X is in the convex hull of A, when X, 1 is in the cone generated by A cross 1, right? X, 1 is in this cone in the vector space V cross R. And since any subset of A cross 1, so now I use the conic version, right? This vector space V cross R has dimension n plus 1, of course. And now by A, I know that there is a subset of A cross 1, which is of cardinality at most n plus 1, such that X, 1 is even in the cone generated by this subset. But this subset must be of a form, I mean any subset of A cross 1 is of a form B cross 1, B cross the singleton 1, for some B subset A. So A yields that there is some B subset of A with cardinality at most n plus 1, such that X, 1 is in the cone B cross 1. And now I go back. If X, 1 is in this cone, I know by remark 10.1.11, applied in the other way around, so we get that X is in the convex hull of B. So I apply it to B instead of A here. Yeah, so that's so in this sense, I get when the affine version or the version for convex sets. Okay, so now another easy lemma. So if S is a compact subset of R to the n, then the convex hull of S is compact. Okay, so yes, convex hulls of closed sets, by the way, need not to be closed, right? I mean, convex hull of bounded sets must be bounded, that's clear, right? Because a bounded set is contained in a big ball, right? And the ball is convex. So convex hulls of bounded sets are bounded, but the problem is that convex hulls of closed sets need not to be closed. I think we had already an example. If you take in the plane, you take a half space like this, right? And plus an additional point. So the union of this singleton here times with this half space, that's closed, right? And but a convex hull, I think I mentioned this already today, looks like this, right? And so it's not closed. Okay, good. But it turns out that convex hulls of compact sets are compact. So that's good. So how do we prove this? So let me call delta a set of all n plus 1 tuples of non-negative real numbers that sum up to 1. And yes, and when the set, maybe I should actually call this, that's okay, but notation is terrible here. I should call this lambda, right? Tuple lambda. And I would like to change this in the lecture notes also. Okay. And then, so you can easily imagine that is to form convex combinations, right? And I have n plus 1 tuples because of Karateodori's theorem that says for convex combinations I need n plus 1 if n is the dimension of a vector space. Now our set delta cross n Sn S2n plus 1, so that's really a power of S, so that's the set of all n plus 1 tuples of elements of S, so it's a n plus 1 tuple of n tuples, right? The elements are n plus 1 tuples of n tuples. So you can identify this with an n times n plus 1 tuple. And when I have here this n plus 1 tuple, so all in all, that's a subset of R to the n plus 1 plus n times n plus 1. This is bounded. That's clear because S is bounded, right? And it's closed. That's also pretty clear, right? Because this is closed, and yeah, very easy to see because S is closed. And therefore it's compact, okay? And by Karateodori, by the version for convex sets, we have that the convex hull of S is the image of this map, right? And yeah, the important point here is that n plus 1 things are sufficient, right? So in these non-negative linear combinations, or in these convex combinations, it's enough to have n plus 1 summons, okay? And that's why the image of this map is really the convex hull of S. And since this map is continuous, its image is compact, but if you have a continuous map, when the image of 7118, the image of quasi-compact space is quasi-compact, and here everything is Hausdorff because R to the n is Hausdorff, so it's compact. Okay, we need one more lemma. Okay, so let V and W be finite dimensional real vector spaces, and when we have this unique vector space topology, right, and on V and W, so we equip it with this unique vector space topology. That's one induced by all linear forms. So that's the coarsest topology making all linear forms continuous. And now take a continuous function from V to W, such that the pre-image of a singleton set with 0 is the singleton set with 0. So that means two things, right? That means that 0 is in the pre-image of 0, so that means f of 0 is 0. And it means that if f of little v is 0, then v must be 0, right? So it's two things, right? So, f, I didn't say that f is linear here. F doesn't have to be linear, right? If f were linear, then this would just mean that the kernel of f consists just of a 0 vector, then this would mean that f is injective. But that's not what I mean here, because f need not be linear. So it means that f of 0 is 0, and whenever a vector is mapped to 0, it's the 0 vector already, right? So suppose there exists a positive real R such that f has some kind of homogeneity with respect to R, so some kind of R homogeneity, namely for all vectors v in V and for all non-negative scalars lambda, f of lambda x is lambda to the R f of x. Right, so if f were a linear map, then this would be fulfilled with lambda equal 1, of course, right? and it would be fulfilled for all lambda real, not just for the non-negative ones. But here I need it only for the non-negative ones. Okay, and also because lambda to be R should be defined, right? I take lambda to be non-negative, also because of that reason, but anyway. Okay, so yeah, it's kind of a homogeneity condition. And we will employ it with R equal 2. So in our application, R will be just 2. But I formulated it in a more general way. And then here I say that phi of V is closed in W. The image of, sorry, that must be F, of course. The image of F is closed in W. Okay, so make both V and W into normed vector spaces by fixing arbitrary norms, and then these norms, of course, also define a topology, and that's, of course, the unique vector space topology. So I have now normed vector spaces instead of topological vector spaces. So the norm is a good tool for us, actually. Okay, so now take, in order to show that this is closed, since we are in a normed vector space, we can, of course, as you know, check whether a subset is closed by looking at convergent sequences. So I take a convergent sequence in this subset, and if for every convergent sequence in this subset, its limit is again in the subset, then the subset is closed and vice versa, right? Okay. So I take a convergent sequence in f of v. Now, how does that look like? Well, the elements of f of v are of a form f of x, where x is in v. So actually, such a sequence is given by a sequence in v, and then f of x. So if I have an arbitrary sequence in v consisting of the x k's, then the f of x k's are arbitrary sequences in f of v. So I take a sequence in V, and I suppose that the sequence formed by its images converges in W. Okay, and now we show that we have to show that this limit is again in the image. Now, since 0 is mapped to 0 by F, we can without loss of generality, we can suppose that y is not 0. Because if y is 0, then it's of course in f of v, right? Because 0 has a pre-image, namely 0. It doesn't play, it's not important that it's 0, but there is something that's mapped to 0, right? Okay. And so, yeah, so it's clear the case where y equals 0 is trivial. So let's suppose without loss of generality that y is not 0. But if y is not 0, then you know just finitely many of these f of xk, right? Only for finitely many indices k, f of xk can be 0, of course, right? Because because this sequence of the f of xk's converges to something non-zero. Okay, and then I could, of course, and I could, of course, discard some finitely many. So only for finitely many xk, f of xk can be 0. And I could just discard these xk's, right? That wouldn't change anything for the convergence, of course. If you want, you could say only for the indices k equal 1, k equal 7, k equal 15, f of xk is 0 when I start my sequence at k equals 16, for example, right? And when so I can, without loss of generality, I can say all f of xk are non-zero, right? Let's right away say that all f of xk are non-zero. And when all xk are also non-zero, right? Because if some xk were 0, then f of xk would be 0, because 0 is mapped to 0, right? And so all xk are non-zero. Now, okay, so now let's look at the following continuous function, which goes from the unit sphere in the normed vector space V, which is of course compact, right? Into real numbers and maps x to a norm of f of x, right? That's the norm in V, and that's the norm in W, of course. And that's, of course, since norms are continuous, that's, of course, a continuous function, okay? And 0 is not in the image of this function, because only 0 is mapped to 0, right? So if 0 were in the image, then, so if we had an x here on this unit sphere, which is mapped to something of norm 0, then, the f of x would have to be 0, and then x would have to be 0, right? Here I use that only 0 is mapped to 0. Then, but 0 is not on a unit sphere. So 0 is not in the image, so h is positive on the whole of S, right? In each point of S, h takes a positive value. So h takes only positive values, but S is compact. So there is positive epsilon such that h is greater than or equal epsilon on S. Now, the norm of the f of xk's is, I do a little trick to, xk divided by its norm. So I use now that xk is never 0, right? So I can divide xk by its norm, and therefore I get on the unit sphere. So this will be now on the unit sphere, right? When I apply f and when I take the norm. So, and that's actually, okay, so, at first I would write it like this. So I have here norm of xk. And when I pull out, or maybe I write it here, right? Norm of xk. And when I pull it out here with norm of xk to br, and when I pull it out from this norm, and I get that's norm of xk to br times this. So here I use this homogeneity condition. And now this is, this is in the image of H, of course, because that's in the unit sphere, right, of V. So so this is greater than or equal, this is always greater than or equal epsilon for each k. And so this is greater than or equal the norm of xk to br times epsilon. And now the convergent sequence of the f of xk's is, of course, bounded. Convergent sequences are bounded, and thus, now you see that also this is bounded. Now, since epsilon is positive, that means also the norm of the xk's to br are bounded, but that means that the norm of the xk's are bounded. So that means that xk itself is bounded, okay? And, every bounded sequence in a finite dimensional normed vector space by the Bolzano-Weierstrass theorem has a convergent subsequence. Now, again, we could, just take with subsequences from the beginning, right? So without loss of generality, in fact, now you could suppose that xk is convergent, right? So because we could exchange the sequence xk by the subsequence, and everything works again the same way. So the sequence xk is without loss of generality convergent, and call x its limit. That's an element of V, right? And now y is still the limit of the images of the xk's. But since f is continuous and this limit of the xk's exists, this is f of this limit. But this limit is, I have called it x, and it was an element of V, and so it's f of x, and that's, so y is some f of x, so it's in the image of f. Sorry, it's not phi, it's f here. Okay. And that's what was to show, right? Here it should also be f, sorry. Probably, I took this from my lecture on polynomial optimization, and I don't know, maybe it was called phi in that lecture, but here phi denotes always my states, so maybe I made f out of it. Okay. Good, so now using this, we will be able to prove the following. We will be able to prove that truncated quadratic modules are often closed. Namely, so let t and m be non-negative integers, g and m tuple of polynomials in n variables x1 up to xn. Suppose that a basic closed semi-algebraic set S of g has non-empty interior, not non-empty, sorry. Has non-empty interior when md of g is closed. Okay. Yeah, so that's closed, of course, MD of G is a subset of a vector space of polynomials of degree at most D, right? And this is equipped with a unique vector space topology. So I think there is no doubt what it means to be closed here. Obviously, M of G does not, MD of G does not change if we discard those gi which are either the zero polynomial or whose degree exceeds D. We have already discussed this in 10.1.6f, right? However, if you discard one of the gi's, S of G might change, right? Not if you discard the zero polynomial, but if you remove a polynomial whose degree exceeds D, then S of G might change, but it can only get bigger if it changes, right? So it will still have non-empty interior, right? So that means we can actually, without loss of generality, we can say that the degree of all gi's is between 0 and D, right? And we set again G0 to be 1. Constant 1 polynomial, and when for all I in 0 to m's, we set again Ri this thing here, that's a non-negative integer, and that's again the floor function, right? And I take the cone generated by the set of all p squared, where p is a polynomial of degree at most Ri, right? That's a cone in the vector space of all polynomials of degree at most 2 Ri. And by Kara-Theodori, we get easily that, that's not Kara-Theodori, by 9 to 1, right, where we define truncated modules. We see easily that, I can write the elements of my quadratic module in this form. Sum from I equals 0 to m Si where the Si's are in the Ci, in the cone Ci, right? So it's in fact exactly exactly how it was defined here, except that here, I did not put the floor, but I could have put it, right? And and so on. But I have non-negative, so in the conic combinations have some non-negative prefactors, some non-negative coefficients, which don't appear here, right? So I don't here have some non-negative lambda ij, but I could take them because, if I have a non-negative lambda ij, I can write it as the square of its square root, and so I could hide it under the square by multiplying pij with it. So that's really the same thing. So if I set, now Caratteori comes into play, so if I set ki to be the dimension of a vector space where these cones live, right, where this Ci lives, we get by Caratteori, namely by the conic version of it, that MD of G consists exactly of following things: sum from I equals 0 to m, sum j equal 1 to ki pij squared times gi, right? So here again, I would actually normally need a non-negative factor here, but I don't need it because I can hide it here in the pij. Yeah, that's by Caratteori. So main point is here, the key point is here that with ki, that I have a bound for this ki here, right? So this is not as in the original definition. It's not an arbitrary number of summons here, but it's bounded by this ki. That's important because then I can write MD of G as the image of a following map. Namely, I take here the Cartesian product of the so Rx Ri is a vector space of all polynomials. Maybe let me so Rx Ri is a vector space of all polynomials in n variables x1 up to xn of degree at most Ri, right? When I take this to a power of ki, okay, so I take ki tuples of such polynomials, right? And I think you can guess what I will do with this tuple. I will build this thing here, right? This thing here. I mean, if you want, you can still put here the parentheses. But also you don't need them, right? And that's the same as this here. Okay, so I use such a tuple to build such an expression here. And then I have to sum up all these expressions, and so I need m plus 1 things like this. And so I have here, a tuple, an m plus 1 tuple of k, whose ith component, or where I start counting by 0 now, is a ki tuple, right, of polynomials of degree at most Ri. And so I'm in this space. And that's a finite dimensional real vector space, this also. And the thing is that this map is quadratically homogeneous, so it satisfies the hypothesis of this lemma with the exponent 2. This map is quadratically homogeneous, that is f of p, so p stands for such a tuple of tuples, right? F of p is lambda squared f of p. Easy to see, right? For all p in its domain, and so domain is this thing here, and all lambda in R. Yeah, and if you can prove that f of p equals 0 implies p equals 0 for all p in the domain f, then and note that, by the way, f of 0 is 0, of course. So if you can prove that f of p is 0 implies p equals 0 for all p in the domain of f, then we will be done by lemma 10.1.14, right? Because the image is then closed. So, right? Okay. So the crucial point is now to see that if f of p is 0, then p is 0. Now, for this, consider the polynomial h, which is product of the gi's. Since the gi's were not the 0 polynomial, right, their product is also not the 0 polynomial. That's actually important. Now, if S of g has non-empty interior by hypothesis, right? So a polynomial which is not the 0 polynomial therefore cannot vanish on the whole of S of g, right? That follows by lemma 2.2.3 because there is a non-empty ball contained in S of g, non-empty open ball contained in S of g, and this non-empty open ball contains a non-empty open cube, right? And by 2.2.3, that was actually much more general. Such a cube is a product of infinite intervals, and if f vanishes on these Cartesian product, when f is a 0 polynomial, right? Okay. So h does not vanish on the whole of S of g. Okay, so there is a point in S of g where h does not vanish, right? But S of g was a set where all gi's are non-negative, right? A set of points where all gi's are non-negative. And now, if I have a point where, in addition to that, h does not vanish, that means every gi is positive, right? At this point. So I get a point in S of g. I get a point in S of g where each gi is positive, and so I get a point. I get a point. In this set, let me go where each gi is positive. Let me call it S prime, right? This set, if it's non-empty, has of course non-empty interior. Okay. Maybe this is even a bit confusing what I wrote here. It's not wrong, but I can. I should say hence S prime is non-empty, right? And maybe I just write hence S prime defined like this: x in S of g, h of x is non-zero, equals the set of all x in R to the n, where each gi is positive. Is non-empty, and okay, good, and we have obviously gi positive on S prime for all I. Okay, That's clear. Okay, so therefore we have well, maybe I should delete this because it's already obvious by what I wrote here. Okay. So if P is in the domain of my map, such a tuple of tuples, which is mapped to 0. So when each Pij, if this is 0 on this set here, right? When each Pij must be 0, of course, on S prime, and since it's open, we have P equals 0. Each Pij vanishes on S prime, so that P equals 0 as desired. Maybe I add something like because S prime is non-empty and open or something. Or because S prime, is open and non-empty. Well, let me see how I put it in the final lecture notes. Good. Okay, so that was this. Now we come. So now we have. So we combine several things. So we combine the original lemma here. So lemma 1, 10, 1, 9. We combine this. With two the two results we had, namely the first result was that convex hull of a compact set is compact. That was this lemma here. And the second one will be the one that we just proved. So the criterion when the truncated quadratic modulus closed. Okay, so we have these two lemmata, and then these three lemmata in fact, and we combine them. Okay, so and it's combined in this theorem here. So let D be a positive integer, M a non-negative integer, and G an M tuple of polynomials, such that the basic closed semi-algebraic set defined by G is compact with non-empty interior. So I have non-empty interior, and I have it's compact. So compact is what I need for this lemma, and non-empty interior is what I need for this lemma. And so I get that the convex hull of S is compact, and I get that MD of G is closed. And so since the convex hull of S of G is now compact, it's also closed, and therefore this I don't need this closure here anymore, right? I don't need this closure anymore here. And of course, as D of G is contains anyway S of G always, right? And so, or contains actually the convex hull of S of G anyway always. Okay, and so actually this becomes equality here. This becomes now equality, right? And here I don't need a closure anymore, right? If I have that S of G is compact, if I have that S of G is compact, and S of G has non-empty interior. Okay, so and that's what I wrote here. That's just what I wrote here. Okay, so and that's my main theorem maybe of this section. It's a criterion. So, you know, I presented with very natural laser relaxation, and I wanted to know when does the best case happen. The best case is that we, as d of g, the projection of a solution set of my LMI onto the X space is exactly the convex hull of the original basic closed semi-algebraic set. Convex hull I need. I cannot, because this is always convex. The convex hull is something I cannot, I unfortunately need anyway. And then, but if S of g is convex, I don't need it, of course, right? So that's, so when is a projection of a solution set of my LMI equal to a convex hull of the original basic closed semi-algebraic set, and of a solution set of my original system of polynomial inequalities. So that's the best case that can happen, and the question is when is it the case? And what I learned here is that it has to do with truncated quadratic modules. If d is my degree of relaxation here, my degree bound, when I take here the d truncated quadratic module associated to g, and I want to know if every linear polynomial non-negative on the basic closed semi-algebraic set lies in it, right? Just the linear ones, right? So we are interested in degree bounds for quadratic module representations of linear polynomials. I mean, we had here, you know, we did a whole lot of work on degree bounds for quadratic module representations, right? Let's see, maybe, where was it? It's maybe no longer here. Yeah, here is one of the theorems, right? That was maybe the main one, in fact, that we had so far on the degree bounds. And yeah, under some Archimedeanity condition and so on. Yeah, when I had this degree bound here, right? But does that actually apply that if f is linear? So yeah, that's so good news is that linear polynomials are always contained in this Rx capital N, because capital N is greater than or equal to 1. Bad news is that you have to look at the distinct zeros of f on S, and they should all be in the interior of S, right? And you see that actually with linear polynomials that will not happen, right? Because I mean, if a linear polynomial has a zero in the interior of S, yeah, when it is a zero polynomial, easy to see, right? So so yeah, so on the other hand, okay, and still, if a linear polynomial could have no zero, yeah, when it might be good for this, when you might be able to apply it for such a linear polynomial, but clearly we need also to consider linear polynomials that have zeros, right? Because we need every linear polynomial which is non-negative on S of g, right? So if this is my S of g, I need to consider a linear polynomial whose zero set is, you know, looks like this. So this linear polynomial will have a zero here on the boundary of S of g, and this zero is not in the interior. So our theorems on degree bounds for quadratic module representations, they are very good, but they don't apply actually. The ones we did here, at least in the lecture, they don't apply, right? So we will have to go back actually and look at what we did in section 9.1. That's not here. We have to go back to our theorems on quadratic modular representations over real closed fields, right? We'll have to go back to these theorems actually. Okay, later, right? That's not in this section now, right? Now, okay, so the proof is now very easy. So we can investigate when does the Lassere relaxation work as good as possible, at least for some degree D, if and only if such a thing holds, right? That's a question on degree bounds for quadratic modular representations of linear polynomials. Okay, so proof. We have that S of G has non-empty interior, so the interior of S of G is non-empty. That's of course contained in S of G, and that's contained in the degree D Lassere relaxation associated to G. And therefore, this degree D Lassere relaxation is non-empty. And then I can apply lemma 10.1.13 and 10.1.15. And then I know that the convex hull of S of G is closed, and that the div truncated quadratic modular associated to G is closed. And our theorem follows from lemma 10.1.9. Okay, good. So this theorem is really good. For practical purposes, it's good to formulate it slightly stronger. It's just slightly stronger. So actually, there is an easy direction and a difficult direction. Actually, if you think about it, the easy direction is from B to A, right? And in some sense, if I want to prove good theorems, if I want to prove theorems that say Lassere relaxation does work, then I just need to go from B to A. And that a large part of this section was to go from A to B, right? But if I want to prove just positive results, I need only B to A, okay? And but I think it's important to know this equivalence. So if you want to prove a negative result, that the Lassere relaxation does not work, that you have here non-equal, then it's good to have A implies B. In the exercise course, we will see such an example. Okay, but so the difficult direction is from A to B. The easy one is from B to A. That direction from B to A is easy. We will see in the proof of this corollary here. Let's now go to a corollary. It starts exactly the same way. The theorem starts with this, and the corollary with the same thing here, what I color in green. And then, one of the two conditions is exactly the same. So condition A is exactly the same, right? And when the following are equivalent, that's exactly the same, right? So now comes the difference. Here we are given a set F, but I color in blue, with this property, right? And let me just argue that for F, I could take one choice of F. F would be just the set of all linear polynomials F that are non-negative on S of G. That would actually fulfill this equation here, right? Why would that fulfill this equation? Well, the convex hull of S of G, we learned that this is compact if S of G is compact, right? So this is compact. So in particular, it's closed. And in our closed convex set is the intersection of all affine closed half spaces containing it, right, in R2Vn. I mean, that follows exactly what I just said. It's more or less this, take instead of this, take here an arbitrary closed convex set and apply exactly as here the separation theorem 735 and so on, right? So yeah, you can do it as an exercise. So you use again this separation theorem here. So you have a closed convex set, and for the other set you take a singleton, and then you get this you get such a k-linear function into the reals, so that such that phi of x is less than or equal r is strictly less than phi of y, where y is this point outside the closed convex set, right? And yeah, and from this that follows, right? Okay. Anyway, do it as a little exercise. We did it essentially that you can take that this blue condition here is always fulfilled for this f, right? So if you take f as the set of all linear polynomials non-negative on S of G when the blue condition is fulfilled, and then condition B actually means exactly this here, right? So in this way you see that theorem 10.1.16 is in fact a special case of this corollary where you take for capital F a set of all linear polynomials non-negative on S of G, right? And so that A to B here holds is trivial, right? Because A to B holds here, right? And so that B to A holds for not just for this special choice of F, but for any choice of F satisfying this. That's useful, and that's why I formulated this corollary. And but that's very easy to prove. Okay, so let's prove it. A to B follows directly from a corresponding implication in theorem 10.1.19 I wrote here. No, it should be, let's see, what was 10.1.9? I don't think that was right. Yeah, okay. Yeah, I should have said here 10.1.16, I guess. Okay. 10.1.16. And for the other implication, suppose that B holds, and let yeah, we know that the convex hull of S of G is contained in SD of G. That's anyway the case, but for the converse inclusion, so suppose B holds, and we have to show that SD of G is contained in the convex hull of S of G. So let X be in SD of G in the degree D Lassere relaxation associated to G, when we claim that X is in the convex hull of S of G. Okay, so since X is in this degree D Lassere relaxation, there is a degree D state associated to G, such that X is the tuple phi of X1, phi of X2, etc. By our hypothesis on F, it is enough to show that f of x is non-negative for all f in f. Okay, so because I want to show, I want to show x is a convex hull of S of g, so I need to show for all f in f, f of x is greater than or equal 0. But if f in f, then by b, f is an MD of g, okay, and hence phi of f is greater than or equal 0, right? Because a degree d state associated to g is a state, for triple. Well, let's look at the definition of states. That was some time ago. Where is it? It's after this example. Yeah, it was here, right? So degree d state associated to g is a state of this triple, right? And yeah, if f is an MD of g, then phi of f is greater than or equal 0. And since f is linear, again, our thing, we have f of x equals f of phi of x1 up to phi of xn. And no, sorry, that's just because x was this. But now, since f is linear, I have this equation here. That's phi of f. That's what I always used here, right? That was my key. How did I say? That was this trivial fact, which is crucial here, right? And phi of f is greater than or equal 0. So I've shown that f of x is greater than or equal 0 for all f in f, as desired. Okay, this corollary is useful if I want to show that the best possible case for Lassé relaxation appears for some degree d, right? Normally you would have to show this, but sometimes you can restrict. Instead of looking at all linear polynomials that are non-negative on S of g, you could restrict to, a subset of these. And let me illustrate with a picture why this can be useful. Well, let's say, so let's say our ZS looks like this, maybe. Okay, so let's say this is our ZS. And the convex hull of S. Convex hull of S would then look like this, right? And now, so that's the convex hull of S. And now the half space is given by these linear polynomials. So one of them could be this. Another one could be this. Another one could be this. Another one could be this, right? Probably I need that one, and so on. Let me draw one in black, maybe. Let me draw another one in green. Right, so these are these half spaces, so maybe I should not draw the half spaces, but just the zero sets of linear polynomials. Okay, so this one, 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 and so on, right? And so I actually wouldn't probably need the following green one, right? But here it would be it would be considered, right? So here I would have to find a quadratic modular representation for the green one, and also for the blue one here. Yeah. And maybe that's not so hard if I have already one for this and for this, right? But it's a bit embarrassing, right? It's a bit embarrassing, and so it's just for practical purposes. It's sometimes better if you have to consider just these things. Okay, and so yeah, say for example you have, make an easier example. You take a circle. So let's say we have here a circle, and we cut out here with a half space. So we have two inequalities, one defining this disk, one defining this closed disk, and one defining this closed half space, right? So a quadratic one and a linear one, let's say. And now I'm sorry, I have problems with the rubber here. Okay, so now your set is this one, right? If you intersect the two, and you get this. So now that's your set. Okay. That's your set, and it's defined by one inequality defining this half space, and then by a lot of other inequalities, right? Defining this half space and this half space and so on. And in this theorem here, I would also have to consider this thing and this thing, right? And this is a bit embarrassing, right? It's a bit embarrassing. Okay, so for practical purposes, it's good to have this corollary. Okay. Yeah, now let's finally take up our example 10.1.4. We consider again the same system of polynomial inequalities as before. And let me draw again, that's this kind of TV screen. That's the unit ball with respect to the 4 norm. And that's such a half space here. And so all in all, the set looks like this. Maybe orange was not a good color to choose. Let's use black. So that's the set in question, right? Okay. Good. As I said, if you want to prove that this black set here, solution set of star, is convex, essentially what you have to prove is that this kind of TV screen is convex. It looks quite obvious, but in fact, if you want to prove it, you have to think a little bit about it. There are several proofs. I already said that, right? Okay. But anyway, it is convex. And now
Now this has given rise to a system of 3 LMIs of sizes 6, 3, and 1 in 14 unknowns, x1, x2, y1 up to y12, right? Let's have a reminder on this. So 6, 3, and 1 in 14 unknowns. So how was it? That was this system, right? One linear matrix inequality of size 6, one of size 3, and one of size 1. So that's just a linear inequality. And you have, what variables were x1, x2, y1, y2, etc. until y12 was the last one, right? So I have 14 variables, 14 unknowns. And we had asked a question whether if you take now a spectrohedron defined by this system square here, and you take the solution set, you take a spectrohedron defined by square, so a solution set of square, and you project it down to the X space, right? Where this is exactly the black set here. Okay. So now we have tools to analyze this now. So translate this into our setting. Translating this into our setting, we declare G1 to be this polynomial, G2 to be this polynomial, and G underscore is G1, G2, and then S of G is the set of solutions of star, and the degree 4 state space associated to G can be identified with a set of solutions of square. I already explained this. Moreover, the just mentioned question just asks whether S of G equals S4 of G. Okay. Yes, exactly. That's it, right? Because S4 of G is exactly this. So this degree 4 Lacerda relaxation associated to G is exactly this projection. We leave it as an exercise to a reader to show that S of G is convex and compact with non-empty interior. I mean, compact is very easy because it's bounded and closed. Convex is a little harder. You have to think how to do it. And non-empty interior is almost trivial. Okay, and then I want, now you see, if you see this red set now, sorry, the black one actually, black one. Now I've lost the axes, I didn't want to lose them. So let me draw the axes again. Yeah, so that's a black set here. And now you can define it using linear matrix inequalities. Well, you could choose all, linear inequalities, right? So you could take all linear inequalities that are all linear polynomials that are non-negative on a black set. And if you take the corresponding affine half spaces and you intersect them all, you get a black set, of course. But that was maybe not the best way to do it, because when you have also to consider this half space, right, this one, and even that one. So you easily see, well, maybe not easily actually, you have to think about how to do it. That, I mean, in the picture, it looks like, okay, you need only this, you need only an inequality defining this affine half space, right? And then you need this one, and then you need this one, this one, right? And all these things here, right? Yeah, okay. And so let's try to make this more formal, what I mean by this. I think I need, or I claim that I need only those linear polynomials, such that, first of all, well, I need G1, right? G1, that's this one here, right? I need G1. And when I need, otherwise I need only linear polynomials that are, that have a common zero with G2, right? So, you know, because they should touch here. So, for example, here, this one has a common zero here. Another one here, right? And so we have a common zero with G2, and their gradient equals the gradient of G2 in this point. Yeah, so the gradient, for gradient actually here, okay. Gradient of G2, I draw it in black at this point, will be something like this. At least it will point into this direction, right? Because it gives the direction of steepest descent, right? Okay, so, and here it will, yeah, and you know, so that corresponds exactly to my picture somehow intuitively, right? But you have to prove this, right? Here, the problem is the picture. The problem is that just assuming that this picture is right and so on and so on. But if you want to prove it formally, and you should do it in the exercise course, then you have to think about how to do this. Okay, good. I should maybe also mention that in some sense I took too many still. So my set F still contains too many things because, you know, I did not exclude that this point X here is here, right? And so I actually took also a linear polynomial defining this half space, right? Which I wouldn't need, okay? But, so I have too many, but that doesn't disturb me. It's just that these, yeah, if everything, my proof will work out. That doesn't disturb me. I mean, I could write here a more complicated condition that this X does not lie in this quadrant here, but it's, or at least not in the open quadrant, but that doesn't, that is not needed, okay? Good, okay, so, and we have to show that S of G is the intersection of his affine half spaces, and yeah, please do this as an exercise. Even in a picture it seems like clear. The corollary 10.1.17, the question whether S of G equals S4 of G is now equivalent to F contained in M4 of G by this corollary, right? It's equivalent to this. Yes, so what we have to show is that F is contained in M4 of G, that we have a degree 4 quadratic module certificate for membership of the linear polynomials in F in the truncated module. And clearly G1, for G1 here, G1 is clearly in M4 of G, right? It's one of the generators of M4 G. Now suppose that F is one of the other linear polynomials here, one of these satisfying this condition. We will then show that F is in M4 of G2 even, right? And then M4 of T2 is of course contained in M4 of G. And that's, you know, now I'm actually don't have to consider anymore G2, okay? G1, sorry. So by 7, 5, 10 and 2 to 4b, this means that there is a lambda, non-negative lambda, such that F minus lambda G2 is greater than or equals 0 on R squared. So why is this? Well, first of all, because G2 has degree 4 and we are looking at a 4 4 truncated degree quadratic module, that f lies in M4, maybe another color is better, that f lies in M4 of G1, G2, actually G2, because I want to prove it lies even in M4 of G2. That's equivalent, because the sums of squares multiplier for G2 can only have degree 0. It's therefore only a non-negative real number, right? So that's equivalent to there exists a non-negative real number such that f minus lambda G2 is a sum of squares of quadratic polynomials. Okay, and now sums of squares of quadratic polynomials are exactly the non-negative polynomials on the plane. That was, okay, so yeah, sorry, that was a bit too fast. So by 2.24b, this means that f minus lambda G2 is just the sum of squares of polynomials. Why? So I don't have a degree bound 2 here anymore, because that is automatic, right? Because f has degree 1, or a degree at most 1, G2 has degree 4, so this is at most degree 4 polynomial. So by 2.24b, I have an automatic degree bound, of course, right? That was this thing here, right? The degree of a sum of squares is 2 times the maximum degree of the things that are under the square. There is no degree cancellation in such a sums of squares expression. Okay, good. And now by 7.5.10, right? We had this very nice theorem about the non-negative polynomials on the plane. These are just the non-negative polynomials on the plane, right? Okay, good. And that was not an easy theorem, right? That was 7.5.10. It was this weakening of Hilbert's 1888 theorem, which we did not prove, and which actually says that a non-negative polynomial on a plane is even a sum of 3 squares, right? We just proved it's a sum of squares. Yes, it was here. So we apply it with the reals over reals, right? F is non-negative on R2. Well, this thing with the degree bound, actually, I could drop it if I use 7.5.9 instead, right? But that's only for homogeneous polynomials, right? Okay. Yes. Okay, so I use this one, and here you could also put the degree bound just like you did here, right? But anyway, okay, I use 7.5.10, this version of Hilbert's 1888 theorem, or a weakening of it. And now, so note that f minus G2, so I have to prove that f minus G2, so f is a linear polynomial satisfying this condition, right? And I have to prove that f minus G2 is non-negative on R squared. Yes. note that x is such an x here is a 0 of f minus g2, right? Because it's 0, 0 of f and of g2. And if I want to, if f minus g2, or sorry, I'm here, f minus lambda g2, x is a 0 of f minus lambda g2, right? No matter what lambda is now, right? But if I want to have if I want f minus lambda g2 to be non-negative on r squared, right? Then with 0, then the gradient, of course, has to vanish in with 0, right? By elementary analysis, right? Because it's a local minimum, right? Because such an x is then a local minimum. So, okay, so I have to, so the gradient of f minus lambda g2 should be 0, right? And so it seems quite reasonable that I take here, that I take lambda equal 1, because when the gradient vanishes, right? Okay, so I take lambda 1. So I try to prove that f minus g2 is non-negative on R2. Okay, let's prove this. And for this purpose, we write f as, let me copy this. So we write f equals a1 x1 plus a2 x2 plus b, etc., etc. Okay, so okay. Good. And we choose point x with f of x equals 0 equals g2 of x, and gradient of f at x and gradient of g2 at x are 0. And when we have that a1 x1 plus a2 x2 plus b equals 0, right? I just plugged in point x into f. And also I plug it in into g2, so it's also 1 minus x1 to the 4 minus x2 to the 4. And also this equation I can write more explicitly. So what's the gradient of this linear polynomial f? It's of course a1, a2. That's the gradient of f at x. And the gradient of g2 at x is, g2 was 1 minus x1 to the 4 minus x2 to the 4. So the gradient at little x is minus 4 x1 to the 3, x2 to the 3. So it follows that minus 4, so now I can plug in, I know that a1 is minus 4 x1 to the 3, and I plug it in here, right? When I get minus 4 x1 to the 4, and I plug in for a2, I know that a2 is minus 4 x2 to the 3, and I plug it in here, and so I get here minus 4 x2 to the 4, right? Plus b equals 0, right? And hence I know that b equals 4 x1 to the 4 plus x2 to the 4, which is 4 because 1 x1 over 4 plus x2 over 4 is 1. Okay? Therefore we have to show that h, which is now f minus g2, I wanted to show, right, that h is non-negative on R2. So let me calculate this a little bit. So that's, a1 is, okay, so a1 was minus 4 x1 to the 3, and then capital X1, minus 4 x2 to the 3 capital X2, and b is 4, right? So b is 4, and then minus g2, so minus 1 plus x1 to the 4 plus x2 to the 4. That's x1 to the 4 plus x2 to the 4 minus 4, x1 to the 3, x1 minus 4, x2 to the 3, x2 plus 3, right? Okay, and I have to show that h is non-negative on R2. It's non-negative on the whole of R2. Now the leading form, the highest degree homogeneous part, is x1 to the 4 plus x2 to the 4, and that's positive definite, right? It's positive definite, obviously. So it's easy to show that f assumes, and then if you have such a polynomial with positive definite leading form, when it's bounded from below on R to the n, right? In our case, R to the n is of course R to the 2, right? But that would work in R to the n, and that's actually easy to show, and that's one of the exercises on the exercise sheet. And now choose y in R2 so choose such a minimizer, right? So choose a y in R2. Okay, it's bounded from below. It's bounded from below, but also you can easily show it actually assumes a minimum, right? Polynomials that are bounded from below not necessarily have to assume a minimum, right? But this one does here. In this case, if it has positive definite leading form, it does. Easy to show, again, easy exercise. By the way, a polynomial which is bounded from below but does not assume a minimum would be that one. That would be a polynomial bounded from below by 0, and which takes arbitrarily small positive values on the hyperbola defined by 1 minus x1, x2 equal 1, right? Because on this hyperbola, this vanishes here, and this gets arbitrarily small if you approach, if you go far out in the hyperbola, so that the x1 coordinate gets close to 0, right? So if you go out here, and but it's never 0. If it were 0, when a point where it is 0 would have to satisfy that the first coordinate is 0, and so it would have to lie on this axis, but on this axis the other term is positive. Okay, but that was off topic, right? So that was to say that if it's bounded from below, you still need an argument why it has a minimum. That's not automatic. Okay, so but now choose a minimizer, a global minimizer of h on R2. Choose a y in R2 such that h of y is less than or equal to h of z for all z in R2. Okay, then I can look at since it's a local minimizer, it's a global and therefore also a local minimizer. We know from calculus that the gradient vanishes there. The gradient of h at y vanishes, but the gradient of h at y is, it's h was this, so the gradient of f at y is let's look at h here. So what's the gradient? So it's 4 times at y is 4 times y1 to the 3, y2 to the 3, that comes from this, and then minus 4 x1 to the 3, x2 to the 3, and we know that this is 0. And now I use that. Now I know that x1. And now I know that 4y1 to the 3 equals 4x1 to the 3, and then of course y1 to the 3 equals x1 to the 3. And now I use that the map t maps to t cube on R is injective. So it's a happy. That seems like that we are very happy now that we can deduce that x equals y. Now, but if x equals y, then 0 equals f of x minus g of x, right? And so both were 0 here, and this is h of x. And yeah, and h of x is now h of y. And h of y was less than or equal to h of z for all z in R2 as desired. Yeah, so maybe I should add something about the injectivity. Maybe I should say here using that R to R T maps to T to a 3 is injective, we deduce this. Okay, that's it. So we could prove that in our example the method works perfectly. Thank you for your patience and many thanks for listening. Goodbye.